Yes? It's muted for the on-screen participant, for the online participants, is that it?
Yes.
Okay.
Okay, it's muted.
It's muted?
Your computer.
Not my computer, it's them that's muted.
Okay, yes, it's there.
It's fixed?
So, it's muted.
So we need to unmute, yep. Ready? Good. All right, good morning. So we're going to take a step back from diffraction and EBSD just at the first part here and just talk about electron microscopy generally. And I'm not going to focus on TEM because I'm not talking a lot about TEM diffraction. So we're just going to talk basically about SEM. So if you've used electron microscopes in the past, it should be very familiar. If you haven't, then hopefully this is enough that it helps you understand what's going on in the SEM. So the reason we would use electron microscopes, there's a lot of reasons. One is for all the analytical capabilities that it offers. But it obviously, when it was first developed, it didn't have all those analytical capabilities, so it was just purely for increased spatial resolution. And as you get increased resolution, you get an increased depth of field as well. So this shows, a micron bar here, 500 nanometers or so, and shows all the features here on this latex spheres, I guess, that I would never look at. But you can see the feature sizes that you can see on a modern scanning electron microscope are down under a nanometer that you can see. The reason for this is because of the resolution equation that includes the wavelength of the radiation that's being used. So if you think of how small of a feature you can see with your eye, it's about 100 microns, about 0.1 millimeters, which is about the width of your hair, right? So you can see your hair nice, but that's because it's all in a long line. If you had a particle that was 100 micron diameter, it'd be difficult to see, but you can probably make it out if you have reasonable vision. Optical microscopy, then you get much less than that, typically down to about a micron or so. This is just saying it's less than the eye, but you're down around the order of a micron or so that you can see. So we go from a nanometer from the electron microscope, a micron for the optical microscope, about 100 microns for the human eye. Radiation of visible light obviously is 400 to 700 nanometers in this rainbow display. Sometimes we just say Roy G. Biv, red, orange, yellow, green, if you've used that here. All right, so the wavelength of the electron beam follows an equation like this, where we have the wavelength is given by a constant value over the accelerating potential plus a term here. This is the conventional way to calculate the wavelength. We also have a relativistic equation, but the results aren't so different until you get very high voltages up 200 kV or higher. So if you calculate this, you can see that the scanning electron microscope, if it's running at 20 kV, which is a standard voltage to use, your wavelength is about 8.6 picometers, something around that wavelength, compared to your 400 nanometers that you get with optical resolution. So it's 5 orders of magnitude difference in the wavelength for optical versus for electron microscopes. And you can see as you go higher, accelerating voltage, that's another order of magnitude, 200 kV, it's about 2.5 picometers. All right, so what happens when the electron beam hits the specimen? So you have this beam of electrons, comes down, it hits the specimen, it interacts. There's a lot of things that the electrons bounce around, some of them bounce out. The electrons sometimes will knock out an electron that's already part of the specimen. It will knock it out, and so it'll come out. Sometimes the electrons will go all the way through, and so you get some transmission signal down here. Sometimes it gets absorbed and you can measure energy coming through there or current coming through the specimen. As you're knocking out electrons out of their orbits in the material you're looking at, it releases X-rays. So you get photons that will come out, and you can measure those and use those for analysis. And there's also optical light photons that come out of your specimen. And you can examine those in a technique called photoluminescence or cathodoluminescence. Used mostly in ceramics and geologic specimens, but you can learn a lot just from the wavelength of the light that's coming out of there. All right, so you have this interaction volume that develops. When you get X-rays coming out of there, it's coming from the lowest part. We call this a teardrop shape. Teardrop shape interaction volume. So X-rays are coming from the lowest part down here, which if you're having 20 keV and something like aluminum, you're probably going 2 microns deep, right? You're getting signal maybe 2 microns into the specimen, something of that order. If you're looking only at backscatter electrons, which are the high energy electrons that come out, so they're approximately the same energy as the incident beam coming in. So if it comes in at 20 keV, comes out at 20 keV, comes out high energy. These come from about 500 nanometers down into the specimen if it's aluminum with 20 keV. Secondary electrons will come from about 50 nanometers, something on that order. EBSD signal comes from just the very top layers. So it's about 10 nanometers of depth penetration where you're actually getting signal when you're doing EBSD work. Okay. At least the EBSD patterns that we see. All right, so how does the SEM work? Just really briefly, you have an electron source, which could be a field emission tip, and I'll show you that in just a minute. It could be a field emission tip, or it could just be thermionic emission, where you have a tungsten filament that you heat up. You're pulling electrons off there, you accelerate them. You actually put them at a high energy as they're up in the gun. And as they pull off there, they pull off towards the ground. So you have an anode that is a donut-shaped anode with a hole in the middle of it, and it's at ground. And so the electrons are accelerated towards that. Some of them go through the hole, through the anode hole, and that's what we use to create the beam of electrons coming down here. The electrons are focused. Since they're charged particles, you can focus them using electrostatic or electrodynamic type of coils. So we have these usually copper coils with specific current that we send through there, and it will focus the beam. The condenser lens, we say, demagnifies the beam, so it basically is what controls your spot size or your probe current in your SEM as you control the condenser lenses. Sometimes there's one, sometimes there's a couple of them. And then you have your objective lens at the end, and the purpose of the objective lens, which again is just copper coils, that is to focus your electrons into a point on your specimen. So you control the beam. You have apertures as well that block out extraneous electrons. Once the beam hits, you get all the signal with the low energy electrons, what we call the secondary electrons, the high energy ones that we're calling backscatter electrons. And then you have detectors for all of these things. The X-rays you have detectors for. So the beam comes down, hits, releases all these signals, and then you can use those signals from whatever detectors you're looking at to measure some signal. Welcome, welcome. All right, so the electron source. Electron source makes a difference in the resolution that you get. So we're going to talk just briefly about electron source. There's actually 3 types of kind of general sources that are used. One is a tungsten filament, and this was written for the microscopes in my laboratory. So we have a tungsten thermionic emission tip where we have a tungsten filament. We run current through there. It heats up to about 2700 Kelvin, something like that, so that the electrons can be released from their work function. So it's a very high temperature. So those electrons can be released. They're at high energy. They see the anode at ground, and they leave their position and head down towards the anode. Right? Yeah, maybe I'll mention this just briefly. The cap, this entire part up here is the cathode. And the cathode has what we call a Vanelt cap. Vanelt also has a hole in it. It's sometimes charged a little bit, just so the electrons will tend towards the center of the hole. So this is negatively charged, this one's charged at ground. But when the Vanelt's charged, we call that the gun bias. So on your electron microscope, you have bias settings, and that's what it is. And as you change the bias settings, you'll get a brighter or a less bright beam, meaning more electrons or fewer electrons coming down your beam. All right, the other general type, well, kind of in between here, is one we call a Lab 6, which is La, lanthanum, and then B, boron, 6, right, sub 6, Lab 6 we call it, lanthanum hexaboride tip. And that will give more electrons than a tungsten filament. And so sometimes we'll put that in. It still works with thermionic emission, but you can get a brighter signal if you have a Lab 6 cathode instead of a tungsten filament cathode. Okay, the other one is field emission, and there's a couple of different types of field emissions. But basically, you have two plates at high voltages. We call these extractor plates. You have your tip down, you're running the current through there. This is a sharpened tip now that you're looking at. So this is the same, your tungsten wire. And then you have a sharpened tip that comes here. And you're pulling electrons just off the very end of that tip. And it's done with a tunneling mechanism, electron tunneling type of a process. And the advantage of that is your electron source is much finer then. Instead of being approximately 100 microns in diameter, your electron source, it comes down to where it's maybe a micron or up to 10 microns diameter. So then your source itself is much finer. All right, and then we work typically in vacuum. I mentioned this a little bit before, not always in vacuum, but typically it's done in vacuum. The reason for that is to minimize the interaction of the electrons, the small particles coming down with any type of air molecules, because they will interfere with the paths of the electrons, interfere with the signal. So you get more of a dispersed signal as you go to a lower and lower vacuum, or a worse vacuum, let's say. Show here a little contamination. Almost all microscopes in universities, you'll get a lot of contamination on your specimen. So as you're imaging, and then you zoom back out and you move to another spot, you see a black square, a black rectangle on your specimen where you were previously imaging. And that black rectangle is hydrocarbons that have built up. So you have an electron beam that's coming down, and then we have all the oils from our fingers or from polishing compound or whatever we haven't washed off the sample good. We're not using gloves all the time, so we get that contamination on the sample. And so as you image, you'll see that spot where you imaged. It's kind of convenient because then you can see where you imaged before. And you can actually, with EBSD, you can see spot by spot where you took measurements. But it's just because of contamination. So with a better vacuum, a clean chamber, you won't see that. But it's pretty typical that we see. All right, so what affects the quality of your imaging? And this is important because, you know, we talk about what the spatial resolution of EBSD is. And to get good spatial resolution on EBSD, you need to have good imaging resolution. Right, so your SEM has to be at the optimum parameters for the best imaging, the best spatial resolution. So we worry about the accelerating voltage, right? What the voltage is you're working with, what your probe current is. Sometimes that's called a spot size on microscopes. Your working distance is important. And then you worry about if you're conductive or if there's any kind of magnetic disturbances from your specimen. If your specimen's magnetic, if you're working with steels and you have a magnetic control of your electron beam, then steels tend to interrupt that magnetic field and tend to cause a problem, right? So you have to know all these things before you're to get the optimum quality. All right, so here's what's suggested. If you have conductive samples, you're usually working at a little bit of a higher accelerating voltage, and that's if you have higher atomic number as well. And we'll talk about what the trade-off is. If you're looking at non-conductive samples, you almost always want to look at lower accelerating potentials to minimize the amount of charging that you get. I'm going to have a slide there, but since I used the word charging, is a buildup of excess charge, excess electrons on a sample. So if your specimen is non-conductive or you don't have it coated with a conductive material, the electrons will come down into your specimen and they won't have any place to go. So then you'll have a negatively charged particle that's coming down and you have a negative charge on your specimen. So it will tend to repel each other, right? The beam will shift and you'll have some imaging issues. All right, looking at spot size or probe currents, this is just some values for the specific microscopes that we have in our lab. But basically, for best imaging, you want a lower spot size, which means your condenser lens current is a little bit higher, meaning you've demagnified the beam as it comes down through the condenser lenses. So this is just, and I don't remember if that's picoamps, it's milliamps, 10 to the minus 8 milliamps, so it's pico. Is femto below pico? What's below pico? I don't remember. It left my brain all of a sudden. Anyway. The spot size is just this setting on the SEM. And so that's what I said. It's specific to this FEI microscope, or now it's Thermo Fisher, is the one who took over this. It used to be Philips Electron Optics. But they just use numbers, 1, 2, 3. It's a condenser lens setting. Okay, so for those online, we're just talking about what spot size means, and it's just specific to a given brand of microscope. All right, so here's just kind of looking generally. If you're looking at a spot size as it goes from large to small, you get your image quality. I don't like that word picture because it's not a picture as such. It's an image that you're creating. But it goes from a poor image to a high image as you go to a smaller spot size. Now there's a problem with this generally because as you have a smaller spot size, you have fewer electrons, so you have more noise in the image. So to actually get a better image, you have to work at a slower scan speed. Right? You can't work at a fast scan speed and still get a good signal. But generally, if we want a good signal imaging in SEM, we'll go to a smaller spot size or a smaller probe current where we can focus the beam, we can control it better to a smaller spot. And then we will scan slowly so that we can get less noise in the image. For EBSD, it's just kind of the opposite. To get good EBSD, we want a larger spot size. But if we're looking at very small grain specimens, we have to have enough spatial resolution, and so then we're going to have to sacrifice, we'll have to be in the middle somewhere. Right? We'll need enough signal that we can get good EBSD, but small enough that we can get inside a single crystallite in our specimen. All right, so here's one just showing a difference in some accelerating voltage. So this is on a nickel 3 aluminum. So it's a good scattering material. 20 kV versus 10 kV. You see the image pretty well here. There's some contrast problems in here where you get the face pointing in different directions. When you're doing secondary electron imaging, which is being done here in the standard mode, the bright surface indicates that it's tilted towards your detector. Right? Makes sense, right? Just coming off, the electrons hit it. Most of them are bouncing, they bounce all over and they're sucked in, so you can see the ones on the pointing away from the detector as well. But it's brighter if it's pointing towards the detector. So on this one, the detector is probably over in this position somewhere. Okay. So you'll see these bright surfaces, and maybe you don't know if that's an indent or maybe it's a pyramid coming up, right? But the way you would know that is to know where your detector is and where the bright surfaces are with respect to that. Okay? Then you know it's an indent instead of a pyramid. All right, so here's a specimen where you have 5 kV, and on this specific instrument, we didn't get enough signal. The detectors weren't good enough at that position. If you go to 20 kV, you tend to go through thin layers. So if you have thin materials, your electrons will go through that layer and will give you information from the backside. So you have some kind of a intermediate value that we're looking for this one specifically. So accelerating potential is going to be an issue for some cases. And just reminding you about the interaction volumes, what's happening. The secondary electrons, these are the very low energy electrons. Maybe if we're coming in with an incident beam of 20 keV, the secondary electrons are on the order of 50 eV. Right? So we go from 20,000 eV to about 50 to 100 eV is what the signal of these secondary electrons will be. The backscatters are going to be close to 20 keV, right? And there'll be a range, a whole spectrum of them, of course. All right, depth of field. Now, according to the resolution equations, to get the best resolution, and this is just optics we're talking about. If we're talking about lenses and visible light, we want a large lens, right? The bigger the lenses, the better, right? We're going to get better optical resolution. Now, for a scanning electron microscope, we don't make our lenses any bigger. We have an aperture, and the signal's coming down through that aperture. So the only way we make it apparently bigger is by moving the specimen up closer, right? And then the half angle coming off the lens is more shallow. And then we get better spatial resolution. So lower working distance gives better spatial resolution. It gives worse depth of field. So if we bring up closer, then we won't see as good of a depth of field. Some people call it a depth of focus, and some people will distinguish between the two, but I don't. In my brain, they're the same. I know it's different. I know you're looking at one side of the lens versus the other, but I use them kind of interchangeably. Okay? So the depth of field is greater if you move away. So if you're looking over several hundred microns, maybe you want to move further away from the image, right? If your specimen's tilted and you want to stay in reasonable focus over several hundred microns, you'll get a larger working distance. If I'm looking at very fine materials, I'm going to try and have as small of a working distance as possible, at least up to where the eccentric position of your microscope is. All right, so in general, we're not designed for low magnification observation. So if you take your SEM and you put in a nice grid, a calibration grid or something, and you go to the lowest magnification setting, you'll see a lot of aberrations on the outside. You'll see a pincushion effect where the lines from your grid will start to curve at the end. It's called this pincushion distortion that you get. And basically that's just from the electrons having to travel a different distance as if they're coming straight down versus if they're going to the side somewhere. Right? So if I have a flat plane, the electron's coming straight down, that's a specific distance. If it's going over 10 degrees, that's a different distance that it's going through. Right? So that's the source of the aberration. So you get your image in focus in a specific region, and usually we're zooming down in quite a bit. And then we try and get a focus, and sometimes we play with the focus knob all we can, and we still can't get a reasonable focus. Hopefully you know about astigmatism, and you can go to the stigmators. And the stigmator knobs effectively are taking your electron beam and making it a circular cross section. So if it's a distorted, I'm having some distorted sound. So if it's a distorted image, so it's not circular, it's coming in as in a distorted shape, then the image will be out of focus as you're focusing. So you take the image down. Usually what I do is I'll play with focus first, and I'll go through focus, and usually the image will stretch in a specific direction. I'll go through focus the other way, it will stretch in the other direction. I'll try and find the minimum position, and then I'll go to the stigmators. And if you have an X and Y stigmator, which we used to always have back in the old days before we did everything with a mouse and a button click, right? Then I would always do the X stigmator, focus again, Y stigmator, focus again, right? That was usually how I get the best image. But the stigmation and the focus definitely are going to be important for spatial resolution while you're doing EBSD. So this is just showing it's not really in focus with the focus knob going this way, not really in focus that way. You play with the stigmators and it goes from this position to this, right? So it brings things into focus. And you play with the stigmators just like you would with the focus knob, right? You're moving back and forth and coming into where it becomes in focus. And if it's knobs or if it's a mouse, I don't know how you do your stigmators. For one of my instruments, I do a shift right mouse click and move back and forth or up and down. That's my stigmator, right? So that's how we do these days. All right, contrast and brightness. This doesn't affect anything with EBSD. This is just your detectors looking at the electrons coming off, right? So to get a good signal, you usually want to bring your signal to where you have a contrast that you're comfortable with. Anything that is too bright in the image, I would say is poor brightness contrast conditions. So anything that, if this was completely white somewhere and washed out, the signal couldn't get any brighter, then I would say you have the wrong conditions. You need to lower either the contrast or the brightness, or play with both of them. All right. So what happens just because of surface roughness in your specimen? You have the electron beam coming down. It's going to be scattering differently. We talked about whether the surface is inclined towards the detector or away from the detector. And you can certainly see that when you're imaging. Anytime you have a sharp corner, you're going to have probably a bright image at that point because you're getting electrons that are spraying off that point. And then you'll have difference. This is just showing these curved lines coming up, the detectors here. So our backscatter, our secondary detector is usually biased. So we are attracting electrons. Remember I said the secondary electrons are 50 eV, around that range. And we can bias our secondary electron detector so that it can attract those electrons. So even if they bounce off and head this way, they'll turn back around and be detected by the secondary detector. All right. Contamination we talked about, non-conductive. Let's just mention a little bit. So if we have this non-conductive sample, so we have the charging effect, there's a couple of things that happen. We get very bright regions, and that's because there's a negative charge that's repelling your negative charged electrons coming in. So you see more of them on the detector because they're less prone to go down inside your specimen. Sometimes as it's moving the image away, you'll see some distortion. You can see some wiggle in the line. If this line's supposed to be straight or a nice curve, you can see some wiggle in this line. A lot of times it will do what we call flashing, where it will start to be bright, and then all of a sudden all those electrons will be carried away by an air molecule inside your vacuum chamber, and it will go dark again, and then that charge will build up and you'll get flashing, so you get alternating lines of dark and bright. So all of those things are indications of charging. And the contamination you just see is this square that you've had there. All right, so what do we do with non-conductive samples? A lot of times we'll coat them. So here's a specimen that was coated with gold, and here's the chemistry of it: bismuth, dysprosium iron, gallium oxide of some type. So non-conductive, looking at it here, you can see some features, but you don't get a nice clear image until you've made it so that you have good conductivity on your sample. Scanning rate affects what's going on with the imaging, so you can have a lot of snow or a lot of noise in the image, and then as the beam is slowed down, all of a sudden, instead of just seeing the image look like you would in a television set or on your monitor, you see a line, and this is supposed to show a line across here. You can kind of see a line there where the image is scanning down. And as it's scanning, you can see that the image has moved, right? It's not scanning directly over the same position. Sometimes there's some drift due to charging. Sometimes there's drift due to mechanical drift. Your stage, especially if it's tilted up, might be drifting. You know, your specimen might be sagging on your carbon tape or something like that. But you'll have a definite indication of drifting as you go to very slow scans. You're right. Now let me bring this up. So these are notes from the electron microscope manufacturer. It's been 20 years ago, but still, as far as what we're looking at, still reasonable. SEM still works the same, right? So, okay. All right, so this is just supposed to indicate that you have some kind of a specimen that's indicated by this green and blue. This is your monitor you're looking at. It's not a very modern monitor, right? It's got maybe a CRT back there. You're scanning the specimen. Your electron beam is scanning across. And as you scan across, you're using some kind of detector that is looking at your signal. And at each point along here, it maps that signal from the electron detector onto your monitor. Okay? So that's how the image is created. Like we said before, if we wanted to go to a lower mag or a higher mag, we would just scan across this part of the specimen. One of the things this is showing is that the electron beam is scanning in the same direction all the time, right? It's always scanning left to right or always scanning right to left, depending on your microscope. And that is to avoid electronic hysteresis, right? So as you scan one way and back the other way, you'll get some hysteresis in the signal. So you won't be at exactly the same signal when you're at the same voltages. So we avoid that by scanning in the same direction all the time. So then you have your image. So you get your image, a lot of different gray levels based on what you're seeing off the detector. All right, so we're trying to figure out what resolution means. So we look at something and we're looking at, if you see this wavelength, if you have a bunch of waves that go under a single particle, you say, okay, I can distinguish that as a particle. When it doesn't go over the single particle, then you can't distinguish that particle, right? So your wavelength is important. Okay, so for the electron microscope, we have the detector. We try and have that so it's scanning over a region, over this fine wavelength that we have with the electron microscope. Comes into the detector and then goes to the monitor that we're looking at. All right, so we mentioned secondary electrons are low voltage electrons coming off. This we're just talking about just throwing me off here. So the secondary electrons created from electrons that have low energy, they're called secondary because we presume maybe they were part of the specimen originally, not part of the incident electron beam, but they could be both, right? And we actually get secondary electron signal from backscatter electrons that hit the specimen, bounce off, hit the wall of the chamber, knock off a secondary electron from the wall of the chamber, right? So we get secondaries from all over the place. If we're doing backscatter electron imaging, then we can get some elemental and topographical information instead of just topographical that we get typically with the secondary detector. And then you can mix detectors. All right, so this is a type of image to look at. And then we say, okay, is this cavities, are these craters that we're looking at, or are they spheres on top of the specimen that we're looking at? Right? You could publish this image and tell me either one, and I would believe you. Right? Both answers wouldn't be right, but you could tell me whichever you want, and I'd believe you. And we talked about how you would know. You can see this is the brighter side of the image over here. It's a little darker here. That's brighter, right? All these have a little bit brighter on this side, a little darker on this side. So that tells us where the electron detector is, right? So where's the electron detector? Depends how you interpret the pattern, right? That wasn't a fair question. So you're saying it's a top, and if it's a top, these are going to be spheres, right? If these are craters, the detector is going to be down here because we'll see the wall of the crater coming down and the wall will be faced towards the bottom. But if they're spheres, yeah, the detector will be up here somewhere, right? So I asked you a question that wasn't a fair question. Okay? So you have to know something about your system to know exactly what you're looking at sometimes. Okay, so this is the same image, just biased differently, right? Same image, different conditions. What happened with that one? We're looking at the same part of the same image. Look maybe at this big sphere here. It's the same one as this one. Now it's flipped upside down. Whoops. Flipped upside down. For that one, you have a setting on your microscope called scan rotation. And if I set the scan rotation at 180 degrees, it just turns the image upside down. It's not changing the image, right? It's not changing where I'm scanning. It's just changing what the image looks like. So I could do it 90 degrees. I could make it look like it's going 90 degrees over. So scan rotation, typically you want to make sure that's set at 0. But I've been messed up a lot of times by having the scan rotation at non-zero, and I go start to work on the SEM and say, well, this isn't working. It's not lined up right, something. Right. That's another setting you have to be worried about. Okay. And then this is the same kind of a question. Are these mesas, are they lifted up, or are they pushed down in? And that's going to depend on where your detector is. Okay. Now this is a detector showing an image of a fracture surface. You see a little particle in there. Right now we're doing a secondary electron image. If we change it to a backscatter electron image, now we get contrast based on elemental composition, based on Z number. If you do just secondary, you mostly get just topographic. So here is the secondary image. Here's the backscatter image. Right, so these are the high energy electrons. They've gone down into the specimen a little further. But the backscattering coefficient for materials is strongly dependent upon the atomic number. And so you see a nice contrast. This different material here, you didn't hardly even notice. Oops, didn't hardly even notice here, right? Just kind of looks like the specimen. But now we see that. And then this is the same image. It's just gone to a mode they call ultra high resolution mode, backscatter. Okay. And then you can map out the different elements using EDS detector, which we're not going to talk about in this class, but okay, and I'm not going to talk about that. So I am done, I believe. I'm going to check what else this shows. It's just showing where all the signal's coming from. We didn't mention Auger electrons. You've probably heard of Auger electrons. Don't say Auger, right? It's French. Auger. Okay, so these Auger electrons, those are the very low energy electrons, and you can look at the loss of the energy from those Auger electrons and determine what element they came from. So I mentioned that backscatter signal might come from 500 nanometers in a piece of aluminum at 20 keV, secondary maybe from 50 nanometers. Auger electrons come from maybe 5 nanometers. It's very surface sensitive. Okay? Bremsstrahlung is just background radiation. And I did mention cathodoluminescence or photoluminescence, where you get optical light signals coming off. Okay, these are just models. Yeah, this is one thing that's going to be interesting here. It's just telling you where the signal's coming from. Skip through here. Okay, so if we have a specific element, say iron, and these are all done by Monte Carlo simulation. If we hit it with 30 kV, we'll get about 3.1 microns of signal, depth signal. Now remember that 3.1 microns, that's just the X-rays that are coming from that deep. You'll never get a secondary signal that deep, right? Secondary's up here. But the signal's coming from much deeper in 30 kV than it is at like half kV. Your electrons, the energy of the electrons is just telling you how fast they're moving, right? So if electron's moving faster, it's going to come down in further before it goes back out. So you can see as you go to lower voltages, you get less information volume, which is good if you have very fine grains. Maybe you can do EBSD at 15 kV, maybe you can do it at 10 kV, still get reasonable results. This is just how the Monte Carlo simulation runs. And then this is showing the same beam energy for materials of different Z value. Right, so if you have a light element versus a heavy element, right? So if you have a heavy element, you're working at a lower accelerating potential, then you get a really fine information volume. Okay. Just some tables. I'm not going to talk about topography anymore. That's the last slide. Running SCM is the easy part, interpreting, understanding, communicating. Okay, so that's the end of this part that we're going to talk about. I'm happy to take any questions that anybody has. How many use electron microscopes here? Just a quick show of hands. More than half? Okay. Okay, I saw a question, please.
For the magnetic samples, for better image quality and better focus, we should focus on which of the aspects, like we call the probe current and also the spot size and also the axis perimeter. So out of this, which one we should focus? And the second part of the question is like the elements swing mode or the secondary electron mode. Which one is better result for magnetic samples?
Okay, so there were two questions there. Talking about if you're using a magnetic specimen, like iron, something like that you're looking at, and you are trying to do good imaging on that specimen, then what type of working distance do you need? Was that the first question? Kind of about working distance?
Yes, working distance, actually I didn't mention, but I mentioned specifically about the probe current and the spot size.
Probe current and spot size, and then you talked about in-lens mode.
Yes, the second part.
Yeah.
In-lens or the secondary electron.
Yeah. Okay, so usually for electron microscopes, they have a immersion lens mode where they create a magnetic field that encompasses the entire specimen. And if you're looking at a magnetic specimen, maybe you've had a mistake like this, like I've made before. where I will turn on that ultra high resolution mode, and my steel specimen will come off of the stub, or it will pull the stub out of the holder and stick to my pull piece. It'll just have a magnet go think, and I'll hear a clink inside my SEM. Go, oh no, what have I done? Okay, so that's something to avoid, right? Going into that ultra high resolution mode when you're at a low working distance and you have a magnetic specimen. Typically, I would try and work.
There is a hand raising during the test.
Okay, there's a question online. Okay, let me answer this one and then we'll go online. So in standard imaging mode, you don't have that magnetic field to worry about. The only magnetic field to worry about is that of the objective lens. And usually that is pretty well shielded. So you should be able to work in standard mode and be able to image without any problems. Now my microscope and most microscopes these days have an EDS mode or an EDX mode. And that is because in the old days for the EDX detector, we had to take all the backscatter electrons out. So we would just put a magnet at the end of the detector, a little donut shaped magnet. And the x-rays would go through and the electrons would get stuck on the magnet. And now if you do that, it will interrupt the magnetic fields of the imaging, so you can't do that. So EDX mode or high resolution mode, you turn those on, that's going to be interrupted by your magnetic specimen. And so you're not able to do proper ultra high resolution imaging on that specimen. There's not a way to get around that. Okay? If you're doing EBSD, that's not a problem because you're not using ultra high resolution mode anyway. That will destroy or distort your patterns, your electron backscatter diffraction patterns. So for doing EBSD, luckily that's not a problem. To get best imaging possible, you do it the same way you would any other material, right? So you have a trade-off between beam energy, current, probe current. You know, you want high probe current for low noise. You want high beam energy for a big information volume. If you have fine features, you have to go lower, and then you have a trade-off. Okay. Okay, did I answer both parts? I think so. Okay. Okay, what's the online question?
I think she is
Okay.
Okay.
Any other questions either online or here? Anybody have more questions? Okay.
So if one and we have optical microscope, other we have electron microscope. Do we have something called X-ray microscope also?
Called an X-ray.
Microscope.
There are dozens of different types of microscopes. So there are X-ray microscopes. There's scanning X-ray microscopes even. They work on all kinds of different principles. I mean, you can't control an X-ray with magnetic fields or electronic fields, right? So it's based on tilting and a slit procedure, right, of how the X-ray microscope works and what you're imaging at exactly. So yeah, there are a number of different. There's scanning acoustic microscopes, right? There's several different types of microscopes.
Resolution is in between optical and electron.
So the question is if the resolution for an X-ray microscope's between optical and electron. Typically an X-ray microscope will have a worse resolution even than a good optical microscope, right? Because you get a lot of spread and it's hard to control the X-rays as well. But then you can get a lot more information as well, right? If you're looking for local stresses, those kind of things, you can get some additional information. Unless you use a synchrotron, and then you can get 3D information, I guess. But okay. Okay, any other questions? Yes.
Can you explain how the gamma texture fiber improve the ductility?
All right, this is a good question. I'm not going to answer it right now, but it's a really good question. So the question is, how does the gamma fiber improve ductility? And we're talking about iron or steel, I presume, right? We're talking about BCC rolling textures. So the gamma texture goes along it's a 111 fiber, right? So you have a 111 that's normal to the specimen. And just briefly, just consider how the slip systems in BCC work, right? Your slip direction is in a 111 type of a direction on a 110 type of a plane, right? So how does that slip need to occur so that you'll have the best ductility? So if you have a 111 in the plane, you have 3 other 111s that are oriented in different orientations of that plane, and those all can move readily in that as I start to deform that in a biaxial stretch, right, which is the formability question you're talking about. When we get to textures and texture components, ask me that question again. And I'm not really going to answer it, but along with Masarovich and the modeling that he's showing, then we can answer that question. Okay? You can go very specifically answer it. But it's basically how the slip systems operate in that orientation.
So, Akanksha, do you have any questions? So you can ask now. Akanksha, who is online?
She's muted.
Yeah, you are muted.
Okay, so I don't hear, but you can type in also if you want.
Yeah, you can type in also. Maybe she has a problem.
Started to feel the pressure. Left the meeting. Going for high tea.
So yeah, we have time. We have time today for IT. It will start at 10:30.
High tea starts at 10:30?
Yeah.
Oh, well,
Yeah.
okay, so I can keep going. I thought I had to take a break
Yeah,
at 1 hour.
Yeah. If you want to take a break, then
I'm okay, but if you want to,
No, it's fine. I think they can go come out and come in. No issues. Okay. And we can start with the second one.
just start.
Yeah.
Okay. Okay, so this next piece that I'm talking about, and don't let me take all of Masarovich's time, or don't let me take any time out of the break. We're gonna spend a few lectures on this topic of indexing patterns. I was going to talk about the difference in EBSD and X-ray measurements. But as I was going through my slides, I realized there's a lot of stuff on texture calculations in there. And so I decided to push that towards more of the end. So we're going to do that later. So we're going to start off with indexing EBSD patterns. There are various strategies to index EBSD patterns. There is online software for at least a couple of different techniques on how to index EBSD patterns. Python is a language that a lot of people are using these days, and there is a platform called Kikuchi.py. Has anybody seen that or used that? Kikuchi.py, so Kikuchi patterns in Python. So a lot of tools that are out there that are available to the public to use. And I would encourage, if you really get interested in doing some work on analytical work on the patterns themselves, to get involved with some of these things. But I do like I do like to show how specifically to index EBSD patterns and what the geometry is and how we play with it. And then I require my students to do it at least once, and I give you the opportunity to do that if you want to take the chance to do that. So this is just an image of geometry. This is something we've seen before. You get your pattern, the beam you consider to be stationary. You get diffraction. On this pattern, we know that the center line of this diffraction, this Kikuchi band, is the exact geometric projection of a plane that gives rise to the diffraction. You can't see it, can you?
Please go to the chat.
There's a question in chat. I can't. I don't have chat. I don't have it. That's inside there on the computer they're using.
No, he doesn't have access to it.
Oh, okay. I can see it here. I see it. Okay. I have a question on optimal resolution and magnification needed to accurately characterize microplastic in soil sample, basically nanoplastic.
What's the question?
So just the accurately characterizing a microplastic in a soil sample. So you have the nanoplastic particles, you have a soil sample, and you're trying to image those nanoparticles within a nanosoil sample. All right, so the best contrast that you get to see those kind of nanoparticles, you have to go to secondary electron imaging mode. All right, so you'd be in secondary electron imaging. Those particles are going to be charging because they're non-conductive. I'm assuming the nanoplastic is non-conductive. So I'm assuming they'll be charging, so they're non-conductive. The soil sample's probably non-conductive as well, but perhaps you can have them so that they are more conductive. But you're going to be working at a low voltage, and you're going to look for the brightness contrast between the particles of plastic and the particles of your soil. So if there's a lot of those particles, you'll probably be able to see them in a soil sample that's been compressed, put in a capsule. You can put powder samples inside the microscope, that's not a problem. But you want to have them compressed. You don't want the powders to be sucked down into the turbomolecular pumps or something like that. But you can go ahead and image, and I would image probably at a very low probe current and accelerating potential, probably 5 keV or less. So very surface sensitive conditions. So hopefully that answers. Okay, so let's go back then. Thank you for letting me know that. Let's go back then to the EBSD geometry. So you have your beam, you have your Kikuchi bands that you have. That's what it looks like in your microscope. It's hitting the specimen, coming over here to your screen or your detector. The image processing is simply just looking at some spot, where your spot is. This is what we call a background image. So you're taking an image over a whole bunch of grains and you get destructive interference. So you just get the brightness gradient. You do a subtraction or a division process depending on how you want to play with the image. And then your raw EBSD image turns into an image that's quite readable. There's a lot of different ways to play with the cameras. I won't talk about that a whole lot, but depending what you're trying to do, if you're trying to very closely measure a D-spacing or very closely measure small angles, you might want to have a low binning. Typically, I would go to 4x4 or 8x8 binning because I'm just looking for orientations of known phases that are in the sample. Okay. There's 1x1, 2x2, 4x4, and 8x8. So you really can't tell the difference by eye too much, a little bit, but not too much. But the computer, if you're trying to measure very specific positions, is important. All right, so indexing. In the early days, we would go in and tell it, here's a 111, here's a 110, and then it would know how to go in and index the patterns. What we've done to do it in an automated way is try and find the positions of all these bands automatically. So to do that, we use a Huff transform or a radon transform. Most accurately, it's called a radon transform, but historically, when Krieger-Lawson did it in 1990, he called it a Huff transform, and we've really just called it Huff transform since then. So what a Huff transform does is it takes a XY point in real space, and all the XY points along a specific line have the parameters rho and theta in Huff space. So if I look at a position, rho is defined as the normal to the line coming down, right? So rho is the distance from some arbitrary origin along a normal direction to the line. Theta is the angle that the rho vector takes as it's coming up from your reference. So this point is part of this yellow line, it's part of this orange line, and it's part of this red line. So that's one XY point that's part of all the rho theta parameters that fit all of these lines. So what we do is we create what we call an accumulator array, and we'll take all the brightnesses for all the different rho thetas, add those up, and we'll have a image in Huff space. This is Huff space here, which is showing this point and showing all the positions that that's going to contribute to. Right? So we'll take the intensity, the brightness of that point, and we'll put it in this accumulator array that is rho that goes positive and negative, and then theta, and we'll put that intensity along all the pixels along that line, that curved line. So we'll have that, we'll create these kind of peaks in here. So you can see sometime like here, for example, this is an accumulator array in Huff space. There's the bright peak. So there's one under here, this bright peak. And that bright peak is right along this line, and it's showing you positions from that intensity, that intensity, that intensity, that intensity, plus all the others along those lines. They all go through that same point, so I know I have a line right there because it's bright. Right, so it's really easy using this mathematics, this Huff transform. It's really easy to pull out the position of your Kikuchi bands because you just go to the Huff array and you pull out points. You say, where's my brightest points? I'll take that one, and you find your bands. Okay.
They also use it in image, say, other than Kikuchi. So
Yep. Yep.
there is an old paper in mathematics.
So the radon transform, the Huff transform are both used in all types of image analysis. That's true. That is true. If you're looking for features in an image, you can find those features. And there's circular Huffs, there's all kinds of different implementations, right? Okay, so here's an example showing just a binary situation where we're looking at these are the bright points in the image. Everything else is black. This is what your Huff transform would look like, right? And that peak is just defines a rho and theta that would define this line. And if we do the entire line, it looks more like that. So we do it for a Kikuchi pattern, an EBSD pattern, and then we can pull out all these. And so this red band is showing this here, this red line. And if you consider the origin in the center, this is the reference, then this is going to be almost negative 90 degrees pointing down here. It's about 90 degrees coming up, and then we're going negative. So if this is rho, positive and negative, we're going about 90 degrees. We're coming down here. That's where that red band is. Same with the green bands, blue bands, whatever. You can go in and identify those. Okay, this is what the raw Huff transform looks like. We put a mask over it, which we call a butterfly convolution mask, because what we expect is bands that are dark on either side and bright in the middle. So if you look at these patterns, we tend to have bright center, and we tend to have these dark regions along the edges of the bands. So we put a mask in to accentuate any features that are dark, bright, dark. Right? We call that a butterfly mask. All right, so this is just looking at Huff transform a little bit. I'm not going to beat this to death. We'll just skip through, but you see the masks, and you can have different sizes of masks if you're looking at different sizes of bands. So if I have a low accelerating voltage, I'll have wide bands, and I'll want a big mask. If I have a high accelerating voltage, I'll have narrow bands, and I'll want a small mask. Okay, so those are settings you can play with in your data collection. Progressive Huff we won't look at, but it basically says, let's start with a coarse set of parameters, and then once we start finding features, let's just do the fine features around that. So it's supposed to save computational time. And then correcting some of the artifacts that are seen. I'm going to skip that as well. All right, now we talk about interplanar angles. We've discussed how to calculate those and how to determine them from Bragg's law, or even just from an equation, how to get the interplanar angles. So what we need to do is we need to find out what our most likely diffraction bands are going to be. So the HKLs of those. So if we have a FCC crystal, all HKLs will be odd, all HKLs will be even if we see anything. So the lowest one's going to be 200, the next one will be 111, right? 111, 200, 220, 311, okay? And then we say, what's the angles between these? And so if you look at the angles, right, you're forming all the possible pairs, these kind of things. You're taking not only the 200, but the 020, the 002, right? So all the families. And then you're saying, what's the angles between those? So now you have all the angles. And then you're calculating what you want to do to index is you want to look at those bands, see what angle they are between each other, and then say, okay, well, that's 25-degree angle, maybe it's this one, right? Or if you say it's a 35-degree angle, well, maybe it's a 111, 220, but it could also be a 311 and another 311, right? So that's what the computer is doing. It's looking these things up. And then it will say, all right, within 5 degrees of 33 degrees or whatever we've measured, we have 3 potential candidates for this band and this yellow band together, right? This pink one and this yellow one. There's 3 possible candidates for those 2 bands. So then we go and we find an additional band, and then we can say distinctly what it is, because then we have that 3rd band plus the other 2 possibles. It's okay. It's okay. I don't need. Okay. I have my water. He loves feeding me tea. I'm not. Okay. Thank you. Okay. All right. If we try and measure this angle directly from here, it's the wrong angle, right? This is a distorted projection. It's not coming up straight. We talked about that a little bit. It's just not the proper angle, okay? So we'll come in, we'll find these 3. We'll say that's what these 3 bands must be, because now instead of finding only these 2 bands, that one that was 35 degrees, we have another one, and we know the angles between those. So now we know for sure it's going to be this pair, and this pair, right? That's these 3 angles, the 200 to the 111, and then these other 2. So we've just done that up because we have this table in the computer of these angles, and we've been able to come in here and measure these angles in the right way, which we'll talk about how to do that. Okay. And then we say, maybe it's not going to be exact, and so we put some tolerance values on, and then we start to vote, and we say, here's one set of triplet of bands, and this is the 3 solutions that maybe this satisfies. Once we give it some tolerance, right? We'll say maybe this will satisfy 3 solutions. And then we'll go in and take those 3 solutions and add all of those to our solutions table. Right, so here's the bands. Here's what solution 1 looks like. These 3 bands fit up pretty nicely. The rest of them seem to as well. Here's the next one. These 3 bands mostly fit up nicely. This one's off a little bit, but it meets our tolerance. And you can see all the other bands are not correct. And the same with this one. These 2 meet pretty good. That one actually meets pretty good. This other one fit our tolerance, so we accept that solution. But it's not the correct solution. We can tell by what it looks like. Okay. So the question is, can you use the bandwidths? And we do try and use the bandwidths sometimes to help clarify. And it's just relative bands that we're looking at. Now, we are going to talk about this more, and I'm going to give you a chance in our lab exercise to actually try and use the bandwidths to calculate a d-spacing. And you'll see that it's just not worth your time. Just not possible.
Bandwidth is, it is not constant because it's higher or lower. It is not constant because of the hyperbola.
The bandwidths aren't constant, right? So you have to go to a specific point on the pattern to measure what the bandwidths are properly. Yeah. Yeah, there's some issues with bandwidth, but difficult to use that to help. It's an option in the software to use bandwidth to help specify the indexing, but I don't use it. It doesn't work very well, at least in the materials that I do. Okay. Now this is the indexing, where you're using the triplets and saying how many of these triplets do we have. We talked about the confidence index and how you have, a certain number of possible solutions. So the number of triplets, if I'm looking at 7 bands, would be 35, or 9 bands would be 84 possible solutions. So if I found all the bands properly, went through all the voting procedure, my top solution should have 84 solutions. Okay. So this is the triplet voting. So here's a set of 3 bands we're looking at. Here's the next set of 3 bands, the next set of 3 bands. This one satisfies this solution. This red, yellow, magenta satisfies 2 different solutions. And then we just vote, and we say solution 1 has 10 votes, solution 2 has 1 vote, solution 3 has 1 vote. So we're going to pick this solution with the most votes. And then we assign a confidence, which in this case would be 10 minus 1 divided by 10. Right? It'd be a 0.9 confidence. All right. So this is just showing you found 5 bands. So these are the ones experimentally determined. They match up with all of them in the correct solution. If I looked at solution 2, probably only 3 of the bands would match up, or solution 3, only 3 of the bands would match up. So we can try and figure out which they are. This one, the blue one, the red one, maybe a green here. Okay. And then we come in and we check the average alignment between the ideal solution and where our calculated bands were, and we call that the fit. All right, so if things line up nicely, we get a fit less than 1 degree. I always look for a fit less than a degree to be happy. And if they don't match up very well, then the fit will be larger than that. And you might get the right solution, right? This looks like the right solution, but probably the calibration's wrong on that. Okay, so that's the 3 voting up. Here's the confidence index itself. So there's the equation that we've talked about a couple of times, and that's what it is for this one we're looking at. Now the confidence index, as it's defined like that, is not a probability, right? 0.9 is not a probability. So this is a curve that was done in a quick way many years ago, but it's been verified pretty much by papers, at least 3 different papers that have verified this curve that is almost universal, assuming you're getting more than 6 bands, assuming you're finding more than 6 bands, and you have either cubic, hexagonal solution, then this curve works out pretty well. And what that's showing you is if I have a confidence index of 0, still could have our answer correct, right? Maybe we're finding 4 bands for solution 1 and 4 bands for solution 2, and so solution 1 minus solution 2 is 0, so the confidence is 0, but it still might assign the right value to the confidence, okay? Confidence is 0.1, 0.2. If it gets above about 0.4, then we say it's almost 100% probability that it's correct. Anything above 0.1 is about 95% probability that it's correct, which means 5% of those are bad. So a lot of times when we're analyzing the data, we'll put in a 0.1 confidence filter, throw out all the data that are 0.1 or below, and we'll still have bad points. But hopefully it's only about 5% of your points that are bad then. And here's an example where we've looked at copper interconnect lines. So there's submicron interconnect lines. That's a 1 micron scale bar. You have a dielectric in between that's amorphous. But when you just do the EBSD indexing, it sees different shades, different intensities of pixels, so it finds bands anyway. The Huff will pull out bands. It will just be garbage solutions. So then we'll say, give us a confidence index of less than 0.3, and it basically throws out almost everything in here. Still have a few stragglers that had a confidence of 0.3. For the most part, all you see now is the metal. All right. So this is just saying if we have bands like this, here's what the confidence index is. We do something we called a confidence, what do we call it? Confidence index standardization, CIS, confidence index standardization. And what this does is it doesn't change the orientation data, right? Changing the orientation data is cheating. Right? We can talk about that later, but it's kind of cheating. But it takes every point within a grain that's defined as whatever your grain definition is. It says these are all within this red grain. And even though that has a 0.3 confidence index, I'm artificially going to make all the points in this grain the same value as the highest confidence in that grain. So now everything just has 0.7 confidence. So when I do the filter, it throws out, then I can, even if I had a 0.3 or a 0.4 filter, this data point would save, and that 0.2 data point would save, and these points would save, right? They're the right orientation, they're just lower confidence. This one would still go away, right? Okay. So playing with that, you can say we're going to keep part of the data, part of them is still correct, but we're not changing the orientations. So this type of cleanup, right, that's a term in the software, in OM analysis software, cleanup. That type of cleanup I usually encourage people to do. Okay, so do the confidence index standardization. And this is just showing, again, we've talked about this one already, where you have 2 patterns on either side of a grain boundary. Grain boundary's convoluted somehow, and the voting scheme is trying to figure out which is the most dominant solution. And it will give you that value. So this is showing that it's actually a twin boundary. So we do fine steps over a twin boundary. That's a 1 micron scale bar. And it creates a pretty perfect grain boundary there, right? There's a red grain, there's a blue grain. You get a couple of these little white points that are incorrect. But if you look at the confidence index, it's highly confident in both grains, but along the boundary, it's not very confident. And that's because it has all these other grains that it's finding. But it doesn't mean they're wrong, it just means they're low confidence. So if you run a confidence index filter, you'll just throw away these few little points here, and all the other points would be saved, instead of throwing away everything that's blue and green inside this.
The boundary is a different phase or?
Boundary is not a different phase, no. This is just a confidence index map.
Okay.
So this is just showing you a confidence of 1 versus a confidence of 0. It's showing the same data. It's not a phase map or something, yeah.
But why it is given no confidence to the boundary?
Right here. You get diffraction from 2 different patterns that get mixed up. So it's going to be finding bands from both of those. So even though it's indexing it like this, there's still these bands in here that it's going to be finding to give it a low confidence, because these bands don't match that solution. So it deconvolutes, but it deconvolutes without confidence. It's saying I'm not confident in the solutions. All right. Now we use these types of analyses also to do phase differentiation. So we're saying, is this a FCC phase or is it an HCP phase? We can look at the confidence index, we can look at the number of votes, and we can look at the fit. These three parameters we can use. And then we put constants out here and say maybe we're going to use 0.5 will be on the confidence index, 0.25 on votes, and 0.25 on fit, something like that, right? So you can make up your own equation to differentiate phases. The reason we do that is because it's not standard. A lot of times just by using number of votes it will be good. Sometimes just by using confidence will be good. But different phases will have different tendencies of confidence, right? If I have a lot of bands, like a hexagonal structure where you have a lot of bands in the pattern, it's more likely, if it finds a bad band, it's more likely to fit an actual solution. So usually your confidence is lower when you have these lower symmetry materials, just by nature of the symmetry. Okay, so this is just showing how it's ranking different solutions for differentiating phases. I'm not going to be, but here's a example where you have, so you've done EDS. Just say, well, maybe it's a MOSI2 or maybe it's MO5SI3. Here's what the fit is for each. Here's what the confidence is for each. And then you got to figure out how to determine which is going to be the correct solution. And the same thing with the other phase. So if we look at this one, we can see that this pattern matches this phase. This pattern matches this phase. So this pattern is a MO5SI3 while this pattern is a MOSI2. Right? And so EBSD can go in and tell you pretty nicely the difference in those. Okay. The more lines you consider, the better off you are if you're looking at especially a low symmetry phase. Typically for cubics, I will use 7 bands. I'll tell people 6 to 8 bands when you're doing cubic symmetries that are really highly symmetric. When I go to hexagonal, I'll use 9 to 12 bands, right? So it's not uncommon for me to use 12 bands. The only disadvantage of using more bands is it takes a longer time to index, right? It's just the amount of time because it has to compare more solutions. So that's really the only disadvantage, is how much longer it's taking. We'll skip through here. You can calculate and you can determine and you can look up in tables what the various intensities of your band should be. We don't do a very good job of matching those directly with what we get in the Huff peaks. You know, this is supposed to be this 3.0 bar 3.0 is supposed to be the highest intensity of the band, of the diffracting band. And maybe it will be and maybe it won't be, but it's a possibility to use the intensity as well. But we don't, I don't anyway typically use that. There are a number of ambiguities. Somebody was asking me about supercells. So that's one of the ambiguities. If we have a material that's tetragonal by a couple of percent, 1%, 2%, then it's going to look pretty cubic, right? We're going to give the algorithm a 3-degree tolerance or a 5-degree tolerance, and then it won't be able to tell the difference between that tetragonal phase and that cubic phase. So there's a number of things like this that are going to make the solution ambiguous. And when that happens, you'll usually get a grain with a couple of different colors in it. Right, so this maybe looks like a grain, but you get a lot of red in there that's maybe a second solution. right? The ambiguous solution. All right. So I was told to stop at 10. Anybody with questions? This was mostly just the image analysis and how the Huff works and how the voting works. This doesn't help you yet to go in and calculate what the solution is, but that's coming up. Yes?
So in X-ray and EM, we see extinction of some poles. Do we see such thing in deviation pattern also?
Yeah, so the question is if you get the extinction bands and the excess bands in the material, that like you would see in a TEM Kikuchi band. Typically you don't see that very well. I mean, the physics is still there that it should exist, but typically what you're seeing is the higher intensity that's between those two lines, right? So the Kikuchi line would be those hyperbolic lines along the side of the bands, and what the Huff transform is picking up is the brighter intensity in between those two bands. So the first algorithms that we wrote for doing Huff transform on these and also on TEM diffraction patterns were based on those Kikuchi bands and trying to find dark and light bands. We always have, remember I said it's bright in the middle and then usually dark on the edges, and that's on both edges. But there is, if you look very closely and do an analysis of a band that you're looking right up close, you can see that effect of the extinction and the excess bands, right? You can see the extra intensity and the lower intensity. But as far as the Huff transform goes, it's ignoring that. Maybe it could be used at some time in doing a better strain measurement or something, but there have been a lot of people that have looked at profiles across the bands and trying to get information coming out of that. That hasn't been very fruitful at this point. Other questions?
Why two different methods used? And your CI also fit. The CI is to calculate the confidence index, to calculate the vote. So why is another method called fit?
So the question is, why do we have both confidence index and fit? And confidence index for me is telling you if the computer has the right solution. Fit is something that tells me if my calibration is done properly. So to me, it's a calibration that I look at for fit for the most part. Now, sometimes when you're doing phase differentiation and you have a bunch of candidate phases, using the fit will also help to determine exactly what the solution is. But for the most part, I ignore fit except for calibration. Okay, I had another one.
So, if we have two structures having the same crystal structure, like benite or martensite, then it is different to differentiate the phases in the previous state. Why is it so?
Yeah. Okay, so the question is, what if we have bainite and martensite, or ferrite and martensite? How do we distinguish those phases? This is another one that there's a lot of papers on, right? Even I have some papers in this area of trying to do bainite and martensite and ferrite. The lattice parameters are all basically identical. They're not, right? I mean, martensite goes tetragonal a little bit, but it's 0.05% tetragonal or 0.1% tetragonal, something. So it doesn't go tetragonal enough that you can actually measure that tetragonality in it. The pattern quality goes down significantly with martensite. So a lot of times people have used the pattern quality to distinguish the phases instead of actually the Kikuchi bands. You're using the quality of the diffraction. And that works really well until you have a deformed specimen. A deformed ferrite looks a lot like martensite when it's image quality. So there's been a lot of people that have tried a lot of techniques. I would say there's probably 30 to 50 papers on that topic. And I'm not sure that anybody has the right solution yet. Although dictionary indexing does pretty good, and spherical indexing that I'm going to get to in some point does pretty good. But using Huff transform to index, it's very difficult to do that.
And for Martin site, one can select BCT phase, and for ferrite, one can select the BCC phase.
You can select BCC or BCT, absolutely, but they're so close that you're going to index them all as cubic.
Almost to the-
Yeah.
Sir, but if we have a very low carbon, like less than 0.18% carbon, then the C by A ratio is equal to 1, then it will be, it will be more difficult than compared to C by A ratio if it is more than greater than 1.
The lower the C to A ratio gets, the more difficult it is to index. That's true. Anybody else? Anybody online that I missed? No. Okay. So I'm assuming then it's 10.
There is one
Oh, we do have one.
What is
Nice.
the minimum CI value for getting good
Ah, yeah, good question. Minimum CI value. So it's almost universal that we will choose 0.1 for cubic and hexagonal materials. So we'll do a CI grain standardization, so CIS cleanup, CI grain standardization. And then we will throw out all the data that are below 0.1. That will give us 95% approximately of the bad data points that get thrown out. So we're still keeping 5% of the bad ones. If we want to get rid of those, then we'll go even higher and throw out everything 0.4 and below. Sometimes when you have a really nice data set, really great EBSD data, it's okay to take your confidence way up to 0.5 or 0.4 or something and throw out everything. But at least for cubics. For hexagonal, you probably could only go to about 0.3. But then just in a standard way, we usually will say 0.1. So there's a button on the software now that you click it and it does all the grain standardization, it does all the confidence index at 0.1, and then it plots up a bunch of maps for you that are kind of the standard maps, just with a single click, which is kind of nice. Okay, any other questions? No. I thought that was a big question, an excited question over there. Okay. Good. Let's break then, and I believe after break we'll have Masarovich back in. So get your tensor brains in, right? Get your tensor brains going. Good. We just now dismissed.
Yes, now we can take a break.
Yeah, I don't know, I'm waiting for someone to tell me to start. Yeah. Okay. So just need a tech guy to show my computer view over there. Yeah. I don't know. Uh-huh. So the computer. Uh-huh. Okay. Okay. So here we are. Okay, so can I start now? Okay. So thank you all for coming. And I would like to thank the hosts here. Well, particularly Samjit Biswas for being such a great host. It's a great pleasure to be here. And I hope this will be useful to you. So last time I've given you 2 links, and I want to repeat those links. If you don't have those notes, well, take a photo now. See, we are addressing, in this series of lectures, we're addressing 2 questions. First, how to translate physics into mathematics for mesoscale problems in 3-dimensional space. And second is how to solve that problem numerically. The second part will be largely up to you, because it's much easier for you to go and do a tutorial and to learn software there than for me to lecture about software. Lecturing about software doesn't, well, it's not very useful. So you really need to try doing it yourself. There is a short tutorial, and at the end of this block, may happen today, may happen tomorrow. Well, I will be giving you sample problem to test what you have learned from these tutorials. But most of these lectures will be focused on this first part. That is how to translate physics of mesoscale into math. Okay, so last time.
Professor, there's one issue. Our institute has a commercial license.
Yes.
I'm afraid it's an old one. I mean, say, I don't remember the version, maybe version 4 or 5. 4.4, right?
Well, is it working?
Well, it works, but it's very old version. So I don't know whether this tutorial I haven't seen.
The details will be mostly in syntax, and if you go, well, on the website they have all tutorials there. So there could be difference that somewhere you put a curved parenthesis or brackets. There will be no fundamental differences, because there you will be using equation-based modeling. So not modules that are built in, but direct equation-based modelings, and we will be deriving those equations here. So let's see what will happen if I go to slideshow. Okay, it's working perfectly. Okay, so I started last time with a fundamental question of continuum mechanics. What is material? What is it that at instant of time t at the position x is moving with a velocity v? So we discussed, and I'm going briefly over what we discussed last time. So this is so-called Eulerian or spatial point of view. So we're looking at a point in space, and material, whatever material is moving through that point, and we look at the small volume around that point. So in standard fluid mechanics, we call it mass continuum, because it is really the mass of that element, this one, rho dV, that we are following now. I cannot get, I should duplicate, yes. Oh, okay, now it's working better. And now I should be able to draw here. Okay, so it's really the mass element rho dV that we're which is currently at x that we're following. Not particular atoms, because we showed in this example of uniform velocity, atoms mix. So this atom may have wandered outside of our element, but the mass of the element remains the same. Okay, so when mass represents material, from there there is a conservation of mass, which I hope you're all familiar with, and there is a concept of material derivative, so some field A which is attached to mass, and you want time derivative but following that mass. So this is not the partial with respect to time. If A is a function of position and time, this is not the partial, because partial keeps the spatial position fixed. It is a partial plus this additional part, or you can write it this way. So it's partial plus this velocity dotted by the gradient of that field. It could be scalar field, tensor field, whatever. And then there is also transport theorem, which says if I integrate over material volume, so this is material volume, so it moves. Material volume changes. So, and I need a time derivative of this field A given per unit mass. So that will be just the integral of rho by material derivative of A, this material derivative. Okay, so, but then we discussed, different case. What about solids? In solids, following the mass does not make sense for the following reason. Mass moves differently from the lattice. Why? You have diffusion. And we discussed briefly mechanism of diffusion. Vacancies and atoms change places, and you get a flux of atoms one way, flux of vacancies the other way. These are complementary fluxes. So you get a motion of mass, but you didn't move the lattice. Now, elasticity of crystals is based on lattice. It's a stretching of lattice. So if I give you motion of mass, that tells you nothing about elasticity. Plasticity too. Plasticity is the motion of one part of lattice with respect to the other part of lattice, like this, right? So you start with an element like this, your dislocation moves on this plane. So this lattice has moved, this part of lattice has moved with respect to this part of lattice. So again, mass moves independently on that. So we need lattice continuum for elasticity and plasticity, and yet we have the motion of mass relative to that through diffusion. What should we do in that case? Well, first we will say our material, since it's lattice continuum, our material is lattice density. So instead of mass density, rho, I will follow the element n dV. So this is the number of lattice points per unit volume, and this is my elementary volume. So it is this n dV that moves with a certain velocity. And then my transport theorem looks the same as before, formally, except that the velocity now has a different meaning. But my material derivative works the same as before. Transport theorem is somewhat different. Now I have material field, means the field that is given per unit lattice density. So this kind of integral, the time derivative of this material integral will be just integral of n by material derivative. So far this is all that changes. There will be other changes, but we'll get to those changes. Now let's typically in solid mechanics we say something like this. Let me look at this picture. This is my this dashed line is the initial position of my body. So this point has coordinate capital X, and after time t it moves into small x, right? So this capital X is called reference configuration and small x current configuration. Well, let's see what is the meaning of that. So we look at our deformation typically for solids, but sometimes in fluids too, as a mapping from initial condition, initial configuration into reference configuration in time t. And we will take without loss of generality that this x is, well, corresponds to t equals 0. So my instantaneous velocity is the rate of change of this position while keeping the reference position constant. What does this mean? Reference position is the name of that material point. Think of it as a name. That's the identity of that point. So I'm following the material, whatever the material is. Is it mass or lattice? So this is my velocity. Well, but the question is, what is this reference configuration? Because at any instant of time, you're looking at a deforming body. Solid or liquid, doesn't matter. You're looking, well, at a particular point. You know the coordinate of a certain point. Where was that point before? And what does that mean? Well, that's a question. We have seen that for fluids, this reference configuration has mathematical meaning, right? I can integrate back in time the motion and find some capital X, but these are different atoms. In that flow process, atoms have mixed. So I'm not following atoms, right? Also, same thing for solids with diffusion. I only have mathematical meaning because, as we have seen in other, let me show you. Yes, we have seen, well, how does diffusion work? This is my grain, for example, and atoms from here diffuse, and I build new lattice here, and I lose this lattice here. So, well, if I look at this point, what is the reference configuration of that point at time 0? It makes no physical sense. I can only give it mathematical sense, right? I can integrate the process back in time. So that is what I call the paradox of the reference configuration. For fluids and solids with diffusion, we cannot attach direct physical meaning to the reference configuration. Only for solids without diffusion, we have that nice picture where material element with all its atoms here at time equals 0 deforms, moves, rotates, and with all its atoms intact into its configuration at time t. That's a nice and intuitive picture. But keep in mind, it's not the physical reality. Now, we can still define, see, if I have a function, if I have a velocity, I can integrate velocity in time and find this capital X. So I do have full mathematical meaning, but be careful about how you interpret physical meaning.
Sir,
Yes?
for fluid and solid with diffusion, is it because this vacancy doesn't have physical form?
No, it's because atoms mix. Right. Well, if you want to look, well, group of atoms moving from time 0 to time t, here, right? Here, from there. Well, that's only if those atoms are fixed to your crystalline lattice and if you move the whole lattice, right? But if those atoms are mingling, well, you can't follow them, right? So if you look at time t and you ask, where does this atom come from? Well, it could be from here, or it could be from somewhere else, right? So your this element here, fluids are mass continuum. So the mass continuum, well, could have looked like this, but the atoms do not come from here. They have been mingling. Same thing with solids with diffusion. Right? You follow your lattice, but not your atoms. So, well, again, if you have a diffusion, right, well, what happens, say you have a grain under tangent, creep, these lattice planes disappear, and here you build new lattice planes. So, well, if you look at this atom, and you ask, where was that atom at time equals 0? Well, could be anywhere. But you can formally integrate in time and get some reference configuration. But keep in mind that reference configuration does not correspond to those atoms.
Sir,
Yes?
thermodynamically there are certain concentration of vacancies, mass, like there are certain atoms are missing. So does that hold for the lattice density n also? If so, how?
I didn't understand the last part.
Does that hold for the lattice density capital N showed the thermodynamic concentration of some vacancy which is for the atoms?
Yes, we have, say you start with equilibrium concentration of vacancies, right?
Yes, that is for mass, but that does not hold for the lattice density.
Oh, lattice density, lattice is not conserved. Mass is conserved, but lattice need not be conserved. Well, if you look at the grain, if you put it, well, under stress, your equilibrium concentration of vacancy will change. If you change temperature, your equilibrium concentration of vacancy change. So your lattice could grow, the number of lattice sites could increase or decrease in time. Also, grain can pick up atoms from another grain, from a neighboring grain. That's a grain growth, recrystallization, right? So the number of lattice sites is not conserved. Mass is conserved for the total system, right? We have only as many atoms as, and they have so much mass. But lattice is not conserved.
And if not conserved means the arrangement in the lattice that is not conserved, means its configuration is not conserved.
Total number of lattice sites is not conserved. So if you put a well, crystalline grain which has n lattice sites, some of those are vacancies. If you put it under stress, it will number of vacancies might increase. If you change temperature, number of vacancies might. So the number of lattice, total number of lattice sites might change in time. Yeah.
So does that mean rho is changing, rho density?
I'm sorry?
So does that mean the density is changing, rho?
No. Those mass density and lattice density are related, right? So if you have, let me try to write here. If you have, well, n atoms per unit volume, and those each atom has a mass m. N lattice sites, and your concentration of vacancies is C, then 1 minus C by m is your rho. Right. But this C and this n, they change independently.
No, my question was about the previous slide. Could you
Yeah.
previous slide? Yeah, here. So when you are going from t equal to 0 to t, you
Yes.
have gone over here. So are you suggesting that the number of lattice sites have changed?
Yeah. Why not?
Right, right? That's
Yeah,
what
you could be changing temperature. You could be putting under stress. Your concentration of vacancies changes.
because you showed a schematic where you had a grain
Yeah.
and then you elongated it, right?
Yes.
So you are suggesting what you are trying to say here is that from time t equal to 0 to time t,
Yes.
the number of lattice sites have changed.
Yes. Not necessarily, but it could change.
It could change.
Yeah. Number of lattice sites is not concerned. Now, I would like to erase this, so I'll have to. Okay, let's try it again.
It should be lattice site occupied by the atom.
Not everyone. There are some vacancies, right?
But what is changing is the number occupied by the atoms.
Yes, that will change too. Yes. So if you add vacancies to crystal, the number of lattice sites increases.
Yeah.
Right.
Number of lattice
Yeah.
So maybe but can you then tell the significance of this difference configuration?
That depends on the problem. In fluids, atoms are mixing, so it's purely mathematical significance. In solids without diffusion, it's full correspondence. It doesn't matter whether it's lattice continuum or mass continuum, you're following the same set of atoms. But if you have a diffusion, then you need to find reference configuration. You will need to compute it, because the difference between current configuration and reference configuration gives you deformation. Right. So if you look at the let's say this part of your crystal has been formed during your creep, right? This is the new part. But you cannot tell what is the elastic deformation of this unless you have reference configuration, right? You have its current shape, but you need to compare it to the reference shape to see how it has deformed elastically or plastically. So that's the usual configuration, usual application. Now, here's the about online question. What is the volume of element under consideration? It's infinitesimal volume, right? We are always looking at infinitesimal volume when we are deriving equations. Now, infinitely many infinitesimal volumes will add up to your whole body, whose deformation you are looking at. But it is infinitesimal volume dV. Okay, that's a formal mathematical procedure when we take some small volume and look at the limit where that volume goes to 0. Okay, so this is a standard solid mechanics and continuum mechanics general formulation. We say we are mapping from the reference configuration, capital X, into current configuration. And here's a picture. This point, this is my origin of the coordinate system, Cartesian coordinates, right? So vector capital X at time 0, and then at time t it is at small x. Displacement here is u, so that's the difference between small and capital X. We think of small x, current configuration, as a function of reference configuration. So reference configuration kind of identifies material. Capital X is the name of that material point. Now, this is a theorem which I make my students derive it, prove it, which I'm not going to do now. We don't have time for that. So I will just state this is a fundamental theorem. There are two unique decompositions of deformation gradient. Okay, I should first talk about deformation gradient. Deformation gradient is the fundamental quantity which tells you everything. All information is there. So it is a tensor whose components are del xi over del xj on this basis, right? Or I can write it shortly like this. So when it acts on element dx, infinitesimal element d capital X, it maps it into deformed element d small x. So if you have this f at each point, you know everything. All information is there.
Just a small question. So how is this deformation gradient different from strain?
This deformation gradient has both strain and rotation.
I see. Okay.
Yeah. So we will use it to get strain. From there, you'll see how we do that. So the deformation gradient has two unique decompositions, and here's probably the answer to your question. RU and VR. This is where U and V are symmetric positive definite tensors, and they do represent a deformation. You will see in a moment what that means. R is a rotation or proper orthogonal transformation. We talked about that. So it is a tensor whose inverse is equal to its transpose. So R inverse is the same as R transpose. And it does rotation. What R does when you apply R to any vector, it just rotates. Yeah. Yeah. Okay.
Rotational unit. R stands for rotational vector.
Yes, it's a tensor, rotational tensor.
Rigid body rotation.
Yes, rigid body rotation. But R can vary from point to point, right? So at this point, it's a rigid body. But its variation in space gives you each point may rotate differently. Well, anyway, here's how it works, and this is the best geometrical description that I could give you. So think of a piece of material, and I'm using 2D illustration because 3D is hard to draw. It's much clearer. So we said U and V are symmetric positive definite tensors. Symmetric positive definite tensors have positive eigenvalues. Who doesn't know what eigenvalues are? So you've all had, eigenvalues. 3 by 3 matrix. So you transform that matrix, or we better talk about tensors. I have symmetric tensor. Now, tensor is a physical quantity, like a vector, right? So whenever I change coordinate system, I get different components. So if I have a rank 2 tensor, its components are matrix, and each coordinate system has a different matrix. The theorem says if I have symmetric positive definite tensor, then there will be one coordinate system where my matrix is purely diagonal. Diagonal. So my matrix U in a particular coordinate system, let's call that particular system U alpha, where alpha goes from 1 to 3, will have form lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0. So if I keep rotating, there will be one coordinate system. This is this coordinate system, where this matrix U will have diagonal form. Those diagonal values are called principal values. Principal values or eigenvalues. Word eigenvalues come from German. Eigen meaning self, own, its own, internal, intrinsic. It's hard to translate German to English. Germans tend to make up words from other words. Okay, and these vectors, these base vectors, these are unit vectors of this coordinate system, are called principal directions or eigenvectors. So I should write that somewhere. Principal directions, or sometimes eigenvectors. Okay, so look at this illustration. The black line and the red line are principal directions. These are fibers, material fibers in principal directions. The green one is arbitrary line dx. This green one here. So we are looking at this operation. F acts on dx. So, and let's first express f in this way. So first u acts on dx. When u acts on dx, it just does stretching of principal fibers. So u will stretch principal fibers. Now this arbitrary fiber will get both stretching and rotation, but principal fibers just get stretching. Then R acts. So I have u acting on capital dx first, and then R acts on that, right? So after u acts, I have this, and then R does pure rotation. This picture is the same as this, just rotated by R. If I do this decomposition, then first my principal fibers, everything just rotates. It's pure rotation into but now those rotated u and v, they're now u1 and u2, they're now v1 and v2 here. And these are principal directions of v. So now v is a stretch tensor, and it only stretches principal directions. But the arbitrary green fiber here gets both stretching and rotation.
B is only for stretching or stretching plus rotation?
For principal fibers, it's only stretching. V will stretch principal fibers, but you cannot stretch principal fibers without rotating other fibers, right? See, if you try to make, just look at here. If you try to make this circle into ellipse by stretching its two main diameters, this arbitrary diameter will both be rotated and stretched, right? You cannot get pure stretching unless the stretching is the same, right? Unless you're deforming circle into bigger circle, right? Then everything is just stretched. But if your stretching in two orthogonal direction is not the same, then some direction in between will get both stretching and rotation.
So only for two biaxial there won't be rotation.
Yes, yes. So now you're guessing already, I hope, that this U and V will be used to define strain. And R is just a rotation. We leave it out of constitutive law. When we define constitutive law, we will connect deformation to stresses, or deformation rate to stresses and stress rate. But we don't want to have a rotation there, because your constitutive law should be invariant with respect to the coordinate system. So rotating coordinate system should not change constitutive law. So this rotation R should not be there. So U or V, mostly U, will be used to define strain. But these are two equivalent decompositions. We could use both U and V. Okay.
Just to go back to that slide, so essentially from this final equation here, we can R equal to that summation.
Thank you for reminding me. I need to explain eigenvalue representation. I will discard this and then we'll do it. Again, I almost forgot something. Thank you for reminding me. See, I showed that it's very important to interrupt me. Okay, so very useful is eigenvalue representation, right? If I can find these vectors, well, eigenvectors U alpha, then my matrix U has the form lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0, right? Or I can write U as the sum, and now notice I'm writing the sum explicitly. There is no summation over repeated indices as we did last time, because I have three of them: lambda alpha and dyadic U alpha U alpha.
Yeah, lambda is a scalar, right?
Yes, lambda is a scalar. Lambda is called stretch ratio. Spelling stretch, CH.
U alpha the vectors.
Yes. U alpha are three orthogonal unit vectors.
So it's like principal strain kind of.
Exactly. Exactly. Now notice this lambda, where lambda is 1, I have no deformation. That's why it's called stretch ratio. It's not strain.
It's not strain.
Yeah. Well, similarly, V can be written on base vectors, on its own base vectors. These are principal directions. This V alpha, sorry, I show it here. V alpha is R tensor dot U alpha. And you can see that from here. Right? These are V1 and V2. Just this rotation transforms U into V.
Just one question. So what is the difference between how U and V?
Yes.
How are these two related, or are they completely unrelated?
They represent the same thing, but on different bases. Right.
Different bases.
So see, think of this same matrix represents V, but on this basis.
The lambdas will remain the same? Again,
Yes, same lambdas.
Okay.
And you can see that from this picture, right? You start from here, you get to the same position whether you go first U then R or first R then V. So whichever decomposition you use, you get to the same end.
But this stretch ratio is also called eigenvalue?
Yes. Yes, stretch ratio, principal values, eigenvalues. It's useful to call it stretch ratio to understand that it's not a strain. Strain is 0 when this lambda is 1. Right, when it's 1, then there's no stretching. It's a ratio between the length. Lambda 1 is the ratio between this length and this length. That's what lambda 1 is. So if it's 1, then there's no stretching. Okay.
Is this valid for large deformation?
Yes, this is for arbitrary deformation. This is why we are doing it, right? It's much simpler to do small deformation. But we need large deformation because for all mesoscale problems, grains move, grains grow, deformation is large, material flows. So you cannot really deal with it using small strains and small deformation. That's why we have to do this.
What is the difference between strain and stretch?
I'm sorry?
What is the difference between
We'll see that in a few minutes. 45. I'll talk, 5 more minutes before I get into, later on there will be a slide where I define different strain measures. Yeah, here, we'll come back to this. Right, we'll get to the question of strain a little bit later. I have some more background here to cover. Now, let's switch to the lattice. Lattice continuum. So, I have a lattice velocity, meaning the element n dV. N is the lattice density, number of lattice sites per unit volume. So, n dV is the total number, is the number of lattice sites in the volume dV. So, that moves with the velocity v. I can define vacancy flux using the difference of the vacancy velocities and lattice velocity. That's the net vacancy flux. That's a relative velocity of vacancies with respect to the lattice. I'm already... No, this slide should be postponed. Let's skip this slide and I'll come back to it later on. There are so many different things to cover, I don't know what to cover first. Okay, let's leave this finite deformation aside and let's move to the formulation. I'll get back to this slide. So let's move to the general formulation and define deformation rates. So if I have a velocity as a function of position, current position, and current time t, I can make a velocity gradient this is just partials of vi with respect to xj. This is delta vi over delta xj. We just write it shortly as vi comma j on the basis ei ej. That's a tensor, right? And it's a right gradient. Now, Symmetric part of that is deformation rate. So this is on the basis EI, this is del VI over del XJ. And this is del Vj over del Xi. Right? Or, I'm sorry, it will be Vi, comma j on basis EI, that's this one. Vj, comma I on the basis EI, that's this one. So this is the symmetric tensor, and it's called deformation rate. Every tensor, or if you want every matrix, every square matrix, can be decomposed into symmetric and skew symmetric, right? So this is all that we are doing. Symmetric part is deformation, and the skew symmetric part, or antisymmetric part, is a rotation rate or spin tensor, which will be called W. If you add them up, right, you get L. So L is D plus W. Okay, now those of you who have done small deformation, who is familiar with small strain definition? Small strain. This is just like small strain. I could use displacements here, but what is displacement? U is just v dt. Well, it's the velocity by small time. So if I have small displacements, I can always make this time interval small enough to make a small displacement here, and I will get linearized kinematics. Small strain theory, which we will get back to soon. But before that, I want to remind you of the concept of stress. Right, we discussed all this. This is just to remind you.
Sir,
Yes.
sir, how do we know that the skew symmetric is the rotation one and the symmetric one is the deformation?
If you rotate your coordinate system, you will find out that this one gives you the same thing. So small rotation, well, in general, when you apply small rotation to a vector, you will need to dot that vector, right? With small rotation. That's the rate of rotation. Well, no, that's not a very good way to prove it. Well, that's the part. If you think of shear, right? I can shear this element like this, or I can shear it like this, right? These are the original lines. So I can just move the top like this, or I can shear, I can rotate these lines. These are two same figures, right? You see that? So if you do it symmetrically, you will find that this change of angle, and this change of angle will correspond to this, the average value. And you will find that the difference between this angle here and this angle corresponds to this. It takes some work, but you'll find it very clearly explained in basic continuum mechanics books. So this is not very difficult, right? So just go to any continuum mechanics book, you'll see those pictures very nicely shown. Okay, two new things to say about stress tensor. First, stress tensor will be symmetric. Well, how do we know? If I apply shear stress, this is sigma 1, 2, and this is sigma 2, 1, right? This element must not be spinning, right? It has to be in equilibrium. So these two guys have to make the same moment, well, about this point. The distances are the same, so sigma 1, 2 must be equal to sigma 2, 1. So those two must be equal, those two must be equal, and those two must be equal, right? Makes sense. Stress is a tensor, so I can write it this way. And one important thing from so-called Cauchy tetrahedron construction, you can show that the traction vector, this is traction vector on any surface with unit normal n. N is unit normal, right? Is n dot sigma. That's what makes stress tensor so useful. If I have stress matrix in any coordinate system, I just need for any surface, I just need the normal of that surface, and I can find tractions, well, on that surface. For future reference, notice that if I double dot symmetric tensor with a general tensor, only the symmetric part survives. You can prove that easily, right? If I write sigma ij and then dij plus sigma ij wij, sigma ij is the same as ji, but w is minus, right? So these will disappear, these will cancel out. So sigma ij dij will be the same as sigma ij lij, right? So we'll need that for future reference, and this is probably a good time to make a break before we start deriving governing equations. Questions? Or applause if you want. I'll take applause. Okay, short break.
box.
Oh,
Online question. Okay, okay.
yeah.
Sir, sir, I have a question.
Yeah.
Like we told, and with V, we can combine another rotation.
Yes, yes. Yes, these on the level of each material point, they're independent, right? So you can stretch the material and then rotate it this much, or stretch it and not rotate it at all, or just rotate it a little. There's no problem there. But the question is, I mean, okay. There are questions on the chat. If you could open them, please. Okay, what's the volume element? Since F has legs in both the configuration, does rules similar to the rotation tensor apply for this tensor? That's rather vague questions. Rules of rotation apply to any tensor, right? So if you're rotating, say, coordinate system. So if a tensor maps tensor A to tensor B, you are in fact rotating both of those. So I think that's that might answer this question. I'm not sure I understood the question.
Hello.
All this is defined in the eigenspace. Yes, these you can write everything. U, V, and R can be written in eigenspaces, right? So you need well, eigenspace of both U and V, right? So to express all three tensors, right? Notice that R is a dyadic to VU, and you have a summation of those dyads. So you need both eigenspace of U and eigenspace of V. I hope that answers the question. Okay. So now is the time for this slide. Let's talk about lattice continuum and diffusion and lattice growth. As we discussed before, when you have creep, you have a lattice growth on the side with a tangent here, and you have a lattice disappearance on the side which is under compression. So the lattice sites here disappear, the lattice sites here are created. Now, well, if I look at instant t, right? Well, I have a velocity of each point, so I can do velocity gradient. There's no problem. I get my velocity gradient density. So that's all good. Well, now, it can be shown that in general, rate of change, and this is material derivative, so this is df over dt, and I should emphasize material derivative. So f dot is L dot f. That can be shown easily. So how will I find my capital X? Capital X is an issue, right? Say, well, I'm looking at this point, and this point has current configuration small x. That's fine. I see it there. But what is the reference configuration of that point? Well, if I have this relationship, And I can always get, at each instant in time, I can get L. I can integrate back in time to get my, I can integrate in time and keep updating my f for each point. So that way, I get a function at time t, f of x and t, tensor function, right? And if I have f of tensor t, I can integrate in space. I can map from dx, from current configuration, back to some reference configuration. Now, as we discussed before, this reference configuration will not have direct physical meaning, but it is useful mathematically. What I really need is this f, right? That's what I need to, this is the important part. I need to follow the deformation, and in each time instant I need to do time stepping and integrate in time. I also need to make some assumptions, because when I create new lattice, that lattice has some deformation gradient, current, right? It also has certain lattice density, and it has vacancy concentration. So what I will assume, and it's a rather physical, reasonable assumption, is that new lattice is created with continuous quantities. So if I have a lattice with lattice density n, the next plane will have that same density. Or if my lattice is stretched, it has certain deformation gradient, the new plane that is created on the top of that epitaxially will have the same stretch, meaning same deformation gradient. And same thing for the vacancy concentration. That's the only reasonable assumption to make. So if I make that assumption, then I'm in good shape. I can define, at least formally, this reference configuration. And I can integrate in time, and each point in this new configuration here, each point, including this point, and this point, they have a value of f associated with them. And if I know f, I know everything about deformation. Yes, yes. It's, no, it's a function of position, right? It, well, just like deformation can be large deformation here, smaller there. Both deformation and rotation they vary continuously throughout the body. These are fields. Tensor field. F is a tensor field. Okay, so one important thing, if I have a assembly of grains like this, one grain, another grain, and I'm making hexagons because they're easiest to draw. This rate of growth of lattice here will be normal velocity of the grain boundary minus the normal velocity of lattice. So lattice is moving, and on the top of that I'm building new lattice, right? So this is lattice growth rate. And if I do that lattice growth rate on a dyad of normals, these are unit normals, over the boundary, delta omega, that's the okay, that's the grain boundary, say for this grain, and divided by total volume, omega, I get a creep deformation rate.
So delta omega is boundary and omega is volume.
Yes.
So delta omega is boundary of a grain or surface area Boundary is what?
surface. Right, omega is a volume, and delta omega is a surface, bounding surface. Delta omega is boundary of omega.
One grain.
Yes, yes, yes. This is one grain.
Total volume.
Sorry,
Omega is total volume.
of the grain,
Okay.
of the grain.
If you integrate delta omega, you get omega.
Yeah.
No, volume and surface area is different.
Yes.
One is 2 quadrant, other is 3 power.
Yes. Yes. Yeah.
How come you can integrate the surface area, you get the volume?
No, you don't get the volume. You get strain. This is non-dimensional. This is strain. Okay. Where is my cursor? So this is this g. That's a velocity. Has units of the velocity, right? So length by time, divided by time, right? This is area. So I have length square, that's length cube, divided by time, and here I have length cube. So it's 1 over time, it's strain rate. Strain is non-dimensional, strain rate is 1 over time, dimensions. So creep deformation rate is a piecewise constant tensor field, meaning that I have one value for this grain, then another value for that grain, another value for that grain. That's mesoscale definition. Now, I can make macroscale definition, but by taking bunch of grains and averaging. And that's what we usually see, well, in experiments, right? In experiments, you're measuring average. But it is a field, but it is piecewise constant. Tensor field. Okay. Now, let's do governing equations. So, governing equations for solids, fluids, whatever, come from balance of linear momentum. So, balance of linear momentum, second Newton's law says the sum of all the forces, sum of external forces, is equal to the rate of change of momentum. So here's my material with volume V, boundary S. In volume V, I have body forces which are given per unit mass, say rho B. B is a vector, right? And rho is a mass density. B could be gravity, right? And on the surface, I have surface tractions. So, sum of all the forces, I integrate surface tractions over surface. I integrate body forces over the volume. This is sum of all the forces. The momentum of
What is small b?
worry?
What is
Small
small b?
v.
B.
B. That's a vector which shows intensity of a body force. Yeah, well, it could be gravity vector. Sometimes it's well, people use vector G for that.
So, what is the
It's force per mass. Right. So it's a force per unit mass. So total force for unit mass is rho b. For unit volume is rho b. So rho b is force per volume. Yes. So rho b dv is the force that acts on elementary volume dv. Yes. Question. Is Vn a function of stress Vn. Ah, that's from previous slide. Vn, yes, but it will depend on stresses, but you need to solve a problem. We are not there yet, right? To find out how it depends on stresses, you need to solve the problem. It's not immediately clear. We'll get there. As CV depend on no, go back. CV, what's CV? As C sub V depend on stress. Concentration of vacancies. Yes, these all depend on stress, but you need to solve a problem to see how. Right. In principle, they will. But for now, right, we need to first formulate mathematically the motion. Right. At the moment, at this slide, we are only looking at the geometry, not the driving forces. So this is still just kinematics. Only in the next slide here, we are starting to deal with forces. Okay. So, yes.
Here we are differentiating between surface forces and body forces.
Yes.
So do we mean like this body forces based on, I mean, the body force acts on each and every element, and the traction acts only on surface elements?
Yes, the most common body force is gravity, right? It acts on every piece of the body. Another force could be electromagnetic force. What else? Inertial forces are also body forces, right? When you're entering the curve with your car, it's pushing you. Every piece of your body wants to make a tangent, right, and fly off. But we are not including inertial forces. We are treating them separately as accelerations. So body force act per unit mass, or B is a force per unit mass, rho B is a force per unit volume. T is the traction per unit surface. They're just traction vector units of stress. So we have sum of all the forces here on the left. Now I need a rate of change of momentum. Well, here's my momentum. Mass rho dv has a momentum mv, so mass times velocity. Rho dv is the mass times velocity. So this is my momentum for this little element, rho dv. Integrating over the volume, I get a total mass. Total linear momentum. And I need the rate of change of linear momentum. And this is where I'm using my transport theorem. We said earlier that rate of change of this kind of integral is just integral of a rho and then material derivative of v, which is, as we know, acceleration. Now, to make this into differential equation, we will need to put everything under the same integral. So we will put everything under the volume integral, right? So see, we have argued before that tractions are nothing but normal dotting the stress, right? We've seen that before. And then we use our divergence theorem. Normal dotting the stress over the surface is the same as divergence of stress, that is del dot stress in the volume. So this integral here becomes del dot stress in the volume. Rho b is already in the volume, and this one I only need to change the sign to put it on the left hand side. And here we are. Now, this has to be equal 0, this whole integral. But it has to be integral, it has to be 0 for any volume, right? I chose my solids like this, but I could have chosen part of it, say like this, and replace the action of the other part with tractions. So this has to be true for any volume. Half volume, this small, tiny volume here. And if you keep following that logic, it has to be true, it has to be 0 at any point, because it has to be 0 for arbitrary volume. So this thing inside the brackets has to be 0 at any point in V, and these are my these are so-called Cauchy equations of motion, partial differential equations, which are equally valid for solids and fluids, for any matter that is moving. Divergence of stress plus body forces is equal to the inertial forces at any point.
Sir,
Yes.
so B basically represents some kind of acceleration, which is easy to understand in case of gravity.
B, think of it as gravity.
Yeah, but in case of gravity, it is easy to understand which acts in downwards always. But in case of other forces,
Well, I mean, how do you know what is downwards? Maybe you are close to Jupiter and your feet are pointing towards Earth.
but if you can think about in general convention, now in this case,
So you would like this to point down.
yes, that acts for all the particles.
Fine.
But
But
in kind of
what does that change?
But in kind of other forces, that may not be the case. So
Yes, electromagnetic forces could act anywhere. Yeah.
yes.
For example, this could be a piece of metal, and you have a magnet somewhere, so those body forces could act in different directions. But that's why we are writing into, well, in a general case, we say there is a vector B, and whatever direction of that vector is, that's fine. So it could be constant, like gravity, or it could be variable, whatever it is. So B is not necessarily constant. For gravity it is, but there are other body forces where this is not constant. It could be changing from one point to another point.
And how about inhomogeneous material? Suppose
I'm sorry?
inhomogeneous material.
Okay, homogeneous material.
This is rho is constant at every point.
If B is gravity,
I'm
that
talking about density rho.
yes.
So rho is not changing with time. It only depends upon position.
It depends if you are deforming the body. Right. If you're deforming the body, you might be stretching it.
Yeah.
So rho is changing. Well, compressibility, right?
Okay. If we are stretching it, means we are suppose doing plastic deformation.
If you're doing plastic deformation, rho will be plasticity by dislocation glide will not change the volume. But plasticity is often coupled with elasticity. In fact, there are almost no problems in plasticity where you can well, there are very few problems where you can ignore elasticity.
So in this case, rho is not changing with time.
That we would call that material incompressible.
Incompressible material.
Yeah.
Okay. And suppose we have these two different materials which are mixed, for example, ferrite plus cementite.
Yep.
It is perlite, very fine perlite. It is mixed. So it is ferrite plus cementite mixed together.
Okay.
So in that case, rho, I don't know, rho will.
The question here is, do you want to represent them together, which I would call macroscopic model. So for macroscopic model, I'm looking at an element of material, right, like this, where I have a little bit of ferrite, little bit of cementite, in mesoscopic models, I would look at a piece of ferrite and piece of cementite, and I'm drawing them randomly here, and I'm looking at a volume like this, which is smaller than your particles, right? So I'm resolving all the fields within the particle. So it depends on which scale you want to model. If you model on mesoscale, then your row will be changing from point to point. If you model on the macro scale, then you're mushing everything together, averaging, and you have one field. Yes, yes. It depends how deep you need to resolve your fields. And that depends, where I'm going with these lectures is towards mesoscale. That is rather fine resolution for, for continuum. But these are the same equations on macro scale, right? Just the quantities have different meaning. How are we doing with time? Any more questions here? Yes. If you do formally balance of angular momentum, right? You have a moment of surface forces, moment of body forces will be the rate of change of the total angular momentum. After much work, you will find, you will come to the conclusion that stress is symmetric, it must be symmetric tensor, which we did intuitively with that little picture of a few slides ago, right, with stress sigma 1, 2 and sigma 2, 1, right, which have to make same moments, right, to keep it in equilibrium. Okay. So let's look at the mathematical structure of a continuum problem, and let's talk about mass continuum. So slightly different for lattice continuum, because lattice density, lattice will not be subject to conservation law. Mass will be. Mass has to be conserved.
So another difference might be lattice then contains vacancy, but
Yes,
mass
yes, yes. Well, that's the same. That's the same thing. Yeah, same meaning. Yeah. So we always start of these those equations that we just derived. Cauchy equations of motion. Well, here they are. They're always the same, but we will pretend that we know something more. So think of adding to those Cauchy equations of motion what mathematicians called closure, and what we engineers call constitutive equations. So if you connect stresses to strains and strains to displacements, then this first order spatial derivatives of stress become second order spatial derivatives in displacements, or velocities if you want. Maybe velocities because we are keeping velocities here. So stresses to strain rates are gradients of velocities. So this will be second order partial differential equation in terms of velocities. That's a useful way of thinking about it. So the so-called strong form of the problem reads like this. Given the initial conditions, that is velocities everywhere at time 0 and mass density everywhere at time 0. Given boundary conditions, and boundary conditions are given in terms of velocities at one part of the boundary, let's call that part SV. And in terms of tractions on the other part, well, of the boundary, later on we will distinguish those two boundary conditions as essential and natural boundary conditions. But for now, let's not get into that why we call them that way. Now, these need to cover whole boundary. I'm also given body forces. So given all that, find the field, velocity field and mass density field, which satisfy this equation, Cauchy equation of motion, with constitutive equations, that is with closure, and mass conservation. Yes. Sorry? H? Oh, ST and SV. So think well, of a body. Here you prescribe displacements, right? So this is SV. And on this other part, well, you prescribe tractions. Right? So this other part will be called ST. And together they form the boundary, total boundary, S.
Why we are dividing that into
because there are certain conditions. How can you prescribe boundary conditions? You cannot prescribe same component of display of velocity and traction at any point. This is just a simpler way of of writing it. You could, in fact, have 6 different subregions where say velocity component 1 is prescribed here and traction component 1 there. Right? You have to have different regions for different components. But you'll find if you try to prescribe both velocity and same component of velocity and traction at the same point, problem will have no solution. It will be ill-posed problem. So we say we prescribe velocities at one side and tractions on the other part of the boundary. There are more complex boundary conditions. You can prescribe linear combination of velocities and tractions, well, some functions, but you cannot directly prescribe both at the same point. No, it's not uncertainty. No. You don't have a solution. Solution will not exist if you prescribe the same 2 things at the same point of the boundary. Yes. Oh, these are boundary conditions. This is our setup of the problem, right? You're solving for your beam. This side is fixed. Here you have some tractions. So you know that a priori. These things are known. You need to solve for the fields inside. Whatever is outside, you are prescribing. Okay. The different approach to this, to the mathematical formulation, is to treat this. Don't go, stay there. Okay, to treat this mass conservation as a constraint rather than governing equation. So it's same formulation. We just don't treat those 2 equations equally. We treat this as the governing equation, and this we treat as a constraint, and we will see the way we apply constraint is via Lagrange multipliers. So for numerical purposes, strong form is not good enough. For numerical analysis, we transform our problem, and specifically for the finite element method, we transform our problem into so-called weak form. I will show you later that strong form and weak form are equivalent. But let's now formulate the weak form, and this is the form, mathematical form of the problem that is used to formulate finite element method. I will talk about finite element method after this. So let's think about all possible variations in velocities. So this point x, right, its actual velocity is v. But let's think of all the field of velocities v plus v tilde, or v wiggle if you want. So the special case where v tilde is 0, that is the actual velocity. Those variations we called virtual velocities. That's what we engineers call them. Mathematicians call them test functions. We look at all possible variations. So they are arbitrary, except where the velocities are prescribed, and they are prescribed on a part of boundary SV where that's where I have so-called essential boundary condition. That's boundary condition in terms of my primary variable, velocities. I cannot vary there. Velocities are prescribed at that part of the boundary. So at that part of the boundary, this field, this vector field, v tilde, will be 0. Everywhere else, it's arbitrary. It could be anything. I will also, and all I require from this field is that the field and its gradient are integrable. That is, when I integrate it over the volume, I don't get infinities. I get some finite number. They could even be discontinuous. They could even have integrable singularities. Okay, so if that is the case, I will also need the Lagrange multiplier which I will, for the moment, I will leave it aside. I will use that Lagrange multiplier to enforce mass conservation, this one, as additional constraint. So, here I can formulate the principle of virtual power, which says that the work of actual tractions and actual external forces and here I have body forces and I have inertial forces. Inertial forces are minus rho dv over dt. So work on that is work rate, that is power. Power expended on those velocities is equal to the internally expended power of internal forces on internal deformation rates. And these are real and these are virtual. So the real forces, the real external forces, expend power on virtual velocities. that is equal to the power expended by real stresses on real deformation rates. Sorry, on virtual deformation rates. I keep mixing that. So, sorry, power of real stresses on virtual deformation rates inside the volume.
Could you, because I'm a bit lost, could you tell us exactly what is it that we are trying to achieve?
We are trying to make integral formulation. So if you we want to make a formulation which will enable us to formulate finite element method, right? That's where we are going, right? We are going to, well, towards formulating finite element method. Finite element method is based on interpolations, so you interpolate between nodal variables, and to get your finite element equations, you need the weak form. At weak form is integral form, which in addition to our unknown functions includes virtual functions or test functions. These are completely fictional. I mean, that's a funny thing it's rather abstract. It's difficult to understand why we are doing that. Only in the end you see the result why we are doing that, right? We will use the arbitrary nature. Why is it called weak form?
Or what purpose does it serve?
It serves to formulate finite element equations.
So, and this finite element formulation is for exactly which problem?
All the problems, any problem you want.
So, in this case, deformation, right?
Yeah, a finite element method is a numerical method for solving partial differential equations. Yeah, for solving boundary value problems, right? I'm sorry?
Finite element methods.
Yes.
Small body and codes and empty nodes and nodes. You are solving with the
No, that approach with looking at small elements, that's the historically how finite elements were developed. But if you have any boundary value problem, you have differential equations and boundary values, you can solve it using finite element method.
Numerically.
Yes, yeah. Yes, numerically. Yes, numerically.
Analytical solution, right?
I'm sorry?
In the absence of analytical closed form
Yes,
solution.
yes.
Okay, so that part I understand.
Okay.
Now,
So to formulate finite element method, you need the weak form. Finite element method is based on the weak form.
yeah, and that's what the confusion is. So what is this weak form?
That's the form which includes your unknown functions and those virtual functions.
So, and what are these two functions? Unknown functions and virtual functions?
Well, actual functions are the functions that you're solving for, like a velocity. And virtual ones are fiction, pure fiction. We dream them up, we use them, and then we will discard them. So they have no physical meaning on their own. We just dream them up. Let's say, let there be some function, whatever it is, and then we will use the fact that it could be anything.
So these actual functions, for example, you said velocity.
Yes.
Is this a variable or a function?
It's unknown function. You can call it a variable, right? Right. It's a function of position and time, right? So it's an unknown variable, but it is also a function of position and time, but it's not known, right?
I want to add something.
Yeah.
Sorry, I'm trying to explain. In the strong form, basically, you have this unknown stress equation. So, strong form, why you call it? Because we need a continuous function. But we cannot solve it. Those are very complex. We don't have exact. So, weak form, we are relaxing the criteria. So, we use this continuous function to solve the problem. So, it makes easier. Like on a computer, you can write as a discrete algebraic. So, this is
Yeah.
We will be lowering the order of continuity.
Yes, yes. So your well, exact solution might look like this. Right, this is, say, function u, but your numerical solution just has those points. So it might look like straight lines, right? So is derivative is discontinuous.
So I cannot see the slide. I don't know.
Ah, sorry. What's happened there?
So now it's better.
Uh-huh.
That one.
Okay, so let me try to make a better picture here. Right. So this is position x. This is your unknown variable v, and your v might look like this, right? But numerically, you're only getting this point, and this point, and that point. So numerically, your function looks like this, right? But you still want it to represent your solution. So in order to deal with these discontinuities, you have to put them under integral, right? Because if you don't, you have a jump in gradient here, right? Yeah. So that's why we formulate the weak form, and it works. It will give you.
The weak form is this straight line? It was started with the strong form?
No. This is the exact solution, and this is numerical solution.
Yeah. Okay.
So this is the weak form. So weak form is a statement. Given initial conditions, essential boundary conditions, and body forces, and well, all the boundary conditions, find velocity v such that for any v tilde, this integral is satisfied. So it's a very funny statement, very abstract statement, right? You need to satisfy that integral for arbitrary v tilde. But it works, we will derive those finite element equations from this very soon. Now, if I want to also enforce conservation of mass, I will use my Lagrange multiplier, and I will add this, which because this has to be 0, right? So then I have for arbitrary v tilde and p tilde, p is Lagrange multiplier. It will turn out to be the pressure. We're not minimizing. See, this is a direct variational statement. Usually, in variational calculus, you have a functional, and you minimize functional to get variational statement. Here we go directly to variational statement. So this may be minimum, may be maximum, may be saddle point, or the functional that is extremized by this may not exist.
So it is not affected by the when you multiply.
No, you will solve for multiplier. Multiplier will sorry. You will get the pressure, but the value of multiplier. Sorry, the value of the multiplier is arbitrary. Yes. Yes, that's why I put this tilde on it. So it's just like those virtual velocities. It's arbitrary. It could be anything.
Suppose three equations, so fraction has three components. The fraction,
Yes.
the three values of the multiplier for each direction.
No. This multiplier multiplies mass conservation equation, right? This is a scalar equation. So I have a scalar multiplier. Yes.
What the whole purpose of this exercise is to find solution for the deformation rating, isn't it?
The purpose of this is to formulate finite element method.
Not the deformation rating.
Not
Not the deformation rating.
that will be part of the solution, right? But my unknown function here is the velocity. Once I have if I solve for the velocity field in time, I can get velocity gradients, then deformation gradients, and everything I need. But I'm formulating the problem to solve for the velocity field.
Why do you need the parallel method?
How else would you solve the problem?
I mean, the governing equation does not have any closed form solution.
Very rarely, for very few, very simple problems. So for most real problems, you have to yes, and to use numerical methods. So for very few problems, you will have a well-analytic solution, and those problems have been solved already.
So this is actually principle of virtual work that we are doing, multiplying with the virtual
Yes.
that function.
Yes,
In principle of virtual work.
yes. Except that I call it virtual power because well, I'm using velocities
Yeah.
rather than displacements. But if you put displacements there, that's virtual work.
That is virtual.
Yes. So this is for those who have studied well, solid mechanics. This is well known. And here's a statement of the principle of virtual power. By force, we mean generalized force. So once when you determine what your primary variables are, and let's say these are velocities, you could have other primary variables, which we will call them generalized velocities. Generalized force is whatever does work on that. So it's a power conjugate of the primary rate. So principle of virtual power says power of actual external forces, including inertia, expanded on the variation of rates. So here are my actual forces, T, B, and inertia, expanded on the variation of rates, these are V tilde, is equal to actual internal forces, here it is, actual stress, expanded on variation of internal rates. And internal rates are deformation rates. And how much time do I have? I'm out of time.
So there are maybe some questions online. There's one question.
Yeah. Yeah, let's see the question.
There was one, but I think he figured out the answer.
Okay, so he figured out. The last thing I want to tell you, and I really want to finish this today, because that will make your question clearer. Why, well, not why are we doing it, but where does it come from? Weak and strong form are equivalent. So start from your Cauchy equations here. Multiply the entire equation with your virtual V tilde and integrate over the volume, where this V is arbitrary except where I prescribe V. So where I prescribe, there's no variation. Now, well, as you integrate term by term here, well, you can write this del dot sigma then dot v as del dot of sigma dot v minus sigma double dot v delta, and let me write this so this is sigma ij comma I, and I want to write it by vj, that is this by this, right? And if I write, well, I can write it as sigma ij vj comma I minus sigma ij vj comma I. Right, that's just a derivative of a product, right? And this part is divergence of sigma dot v, and this part is sigma double dot gradient of v. So I'll keep these two guys together here, multiplying v, but this one goes to the surface using divergence theorem. So this is integral over the surface and dot sigma dot v, and this is my traction, right? And this is, well, sigma double dot v delta, and this one remains the same. These are body forces, including inertia forces. So here we are. This is traction, work of external forces. This is my weak form. I have derived my weak form by taking my differential equation, multiplying it by v and integrating and doing some manipulation.
So maybe a silly question. So the slide starts with S arrow W.
Yeah, so that's strong to weak. So I start with my this is my governing well, differential equation equals 0. I'm starting from differential equation, and I just multiply it with arbitrary function that I dreamed up, and integrate over the volume.
And what is that function that you are multiplying it with?
Whatever you want.
So because I don't see that multiplication.
Here.
Okay, so we did that.
Yes.
So there is equal sign inside integral.
Yes, that's informally written, right? What I'm doing, I have a equals b. Well, I multiply that with v tilde, and I integrate, well, both sides if you want. But to write it simpler, I write a minus b, or if you want, a equals b by v and integral. That's not well correct, but I'm just telling you what I'm doing. I'm taking the whole equation, multiplying it by v tilde. So I got my principle of virtual power, or my weak form, from the strong form. You can also go backwards, and if you do that carefully, you will see how those boundary conditions pop out, and those boundary conditions, they come out, well, in a different way. But we don't need to do that in the lecture now. I will stop here. Yeah, sure.
So from the weak form to strong form, you are again multiplying with the same.
No, to go in the weak form, I already have v tilde. Right. So I start with this expression. This is my weak form.
Right.
Then I will transform this first, using this backwards. It's the same thing, just going backwards. Right. And then I would bring it all I will bring it into this form, and then I will argue because my V is arbitrary, I can vary it independently on the surface and in the volume. And this will give me differential equation, and this will give me this boundary condition. So what I can do, I can go again through this next time. Well, we'll start from this slide. But what I wanted you to understand that these are equivalent forms, right? So this is just a transformation of our governing equations into different form, which will be most suitable for developing interpolation-based numerical method, like finite element method.
Well, these lectures are very loaded, so it will take us some time
Yes,
to digest.
I know. That's why I better stop now. What, you want to take a picture of what? Last slide? Last slide. Where is that last slide? This slide? Well, I'll go through this next time. Any more questions?
What was the closure that you mentioned? Is closure boundary condition?
Closure. These are constitutive laws, right? Because you see, yeah, could be Hooke's law. Well, if you look at the governing equation here, you have 6 independent stresses, right? And you have only 3 equations, right? You can't solve for them. So you need to connect stresses to strains via constitutive law, and then strains or strain rates you express in terms of velocities, for example. And then you have 3 velocities, that closes the problem. Without, well, constitutive law, the problem is not closed. Right. That's why mathematicians call it closure.
So we need the conservation law as well as closure.
Well, constitutive law. The relationship between stresses and strain rates.
Yeah, conservation between stress and the strain rate
Yes.
is the constitutive law.
Yeah, that's the constitutive law or closure.
Or closure. We need closure on addition of the constitutive law.
No, well, it's the same thing. It's just different expression that if
Material scientists or material engineers versus mathematicians.
yes, if you read mathematical literature, you will find the word closure. If you read engineering literature, you will see constitutive equations.
I mean, the finite element formulation was developed by mathematicians, right?
Yeah.
They use the term for closure.
Yes. Same thing for this those virtual velocities. We call them virtual velocities. Mathematicians would call them test function. Also, we call principle of virtual power. They call it weak form.
Which one actually depends on test function? It's okay.
Yes. Yes.
It depends upon
Yes.
test function.
Yes. Okay. Done for today.
So do you teach this in undergraduate program or advanced?
I'm sorry?
Do you teach this in the undergraduate program or?
No, graduate. I'm trying to cover everything, right? To see, we.
Undergraduate mechanical engineers or postgraduate mechanical engineers?
Yes,
or
yes.
Mechanical engineers.
So the goal is to get to the